I would like to introduce our first speaker, Bernd Noack, Professor Bernd Noack from the Harbin Institute of Technology, Shenzhen, China, where he holds the chair of turbulence control with artificial intelligence. Besides, he also holds a honorary professorship for turbulence control at TU Berlin, Germany. Bernd studied physics in Göttingen, where he also did his PhD. And from my point of view, I think Bernd is an outstanding researcher, which can be clearly inferred also from the numerous awards he received throughout his scientific career. For example, if I focus on the most recent ones, Bernd, oh, it's quite hard to say your name in English. I'm sorry. Bernd, I stick to the German pronunciation. You can correct me later on. Bernd received one of the very prestigious Chinese central government National 1000 Talents Awards. Moreover, he belongs to the list of highly cited researchers according to Web of Science. That means he's one of the most cited researchers worldwide, independently of the field. Except that, I want to mention that Bernd is a fellow of the American Physical Society since 2012. And yeah, I first met Bernd in 2019 at the Senior German Symposium for Machine Learning and Data-Driven Methods for Model Reduction and Control, where he not only gave a terrific talk, but I also enjoyed inspiring scientific conversations with him. Hence, I'm very much looking forward to your talk, Bernd, on gradient-enriched machine learning control, taming turbulence, made efficient, easy, and fast. For me, that sounds almost too good to be true. So please, Bernd, explain the details. The stage is yours.
Thank you, Karl, for this very nice introduction. I'm impressed. Thanks to the organizers, Karl, Timm, and to Lasi, for giving me this floor. And I'm happy now to talk about the topic, which Karl mentioned. So I need to start my screen. Share. So can you see me? Good.
Yes, I can see it.
So, wonderful. So today I will talk about gradient-enriched machine learning control, turbulence made efficient, fast, easy, and fast. Actually, I think it's true. And this has been a work done by my recent postdoc, Yixing Li, and by my now finished PhD student and soon postdoc, Guy Corneo Makeda, together with the co-supervisors François Lusarin and Marek Mosinski. This work has been supported by the Harbin Institute of Technology, by the French and German Science Foundation, and by car industry. I will start with a press article from 2006 from Renault, and they were reporting about a car, Altica, which was aerodynamically already very well designed, but they managed to put some active synthetic jet here at the trailing edge, and they could reduce the drag by another 20%. This would correspond to about 1 liter of fuel savings per 100 kilometers. And they claimed that it would only take 10 watts of actuation energy. So quite impressive. They announced it on a car show in 2006, but there were not many customers who wanted to buy this for 3,000 euros. So that's why it died. Nevertheless, it shows the potential of turbulence control. And of course, turbulence control can not only be applied to cars. You can start, for instance, with more simple configurations like a boundary layer or turbulent shear layer or wake flow jet and grid turbulence. We are also working at this moment to reduce the drag of China's high-speed trains, who shall run with 600 kilometers per hour at some point. Skin friction reduction of ships is another opportunity. Then you have wind turbines, aero engines, production, medical applications, and so on. I will stop here. So it has applications of epic proportion. And I will now focus on one example related to the car, so a simple car model, an Ahmed model. We want to reduce the drag. The drag is measured here on this balance. The flow comes from left to right. And we manipulate the flow with 4 slot actuators, independently operated here. The flow is monitored by 12 pressure sensors. Now the name of the game is find a controller from the pressure sensors to the actuation such that the drag is minimized. So if you look at the flow, here you see a simulation, the U component in the background and the pressure on the Ahmed body. You see already in the color code of the U component, you have many high frequency components, you have also many low frequency components. So modeling this flow is quite a challenge. I would say it's impossible. We managed to do this for the unactuated flow with 100 modes, but to do this for the actuated flow is next to impossible. Now the question is, what shall we do? So one approach is a model-based control. Here you see Tien. So he was a student of Van Karman, and he's a co-founder of cybernetics. So he was probably the first person who has applied feedback flow control with control theoretical methods. So the model-based control, you need a model. So you have a plant, a controller. You only know some sensor information. You feed it in the control translates it into an actuation command. And this controller shall minimize the cost. Here in this case, the cost is the drag. Now you try to find a model which has essentially a very similar behavior, has the same sensor readings, have a similar performance. And then you can build a dynamic model. A is a flow state, B is the actuation command, S is the sensor signal as a function of flow state and actuation command. And now with this model, you want to derive a controller, which is only a function of the measured data. So once you have the model, you can derive the controller, and you can put the controller in the original plant. And if everything works well, then you can reduce the drag as much as in your model. This works beautifully if you only have, say, periodic dynamics or few frequency dynamics. So it works in very simple cases, but in case of broadband turbulence, it's practically impossible. How shall we go from here? Well, we can look into nature. Here you see a bald eagle, and the bald eagle can land on a stone under gusty wind condition using his wings as the actuator, and he has some skin friction sensors below. There's also an accelerometer, so he can determine the acceleration in his body, and he can land on the stone with feedback flow control. He can also catch a mice on the field. He can do many amazing flow control maneuvers without going to any of our classes, without learning control theory, fluid mechanics, whatever. So somehow nature has found a way of doing flow control without this model-based path. And this path can be called trial and error, can also be called machine learning control. So it's based on the fact it's very easy to test if a controller works. So you test it, and then you see measure the cost. And now you are putting in more and more controllers, and with a smart trial and error, the performance should become better and better. So now you have replaced modeling by an optimization of controller. So in case of the eagle, it takes millions of years, and many eagles have to die on the way. If you do it in the wind tunnel, you want to be finished after maybe a few hours. And so you have to give it a more algorithmic, fast procedure. What we want to do, we want to minimize the cost. So in this case, the cost is the drag power, and we have to include the actuation penalty. And now we have to solve the regression problem. Namely, we have to minimize the cost for using the best controller. So this is kind of a variational problem, which is very hard to solve. But fortunately, there are very powerful regression solvers. And arguably one of the best regression solvers is genetic programming. What we do here, we have our dynamical system, could be the experiment. We have the controller. We have a fast inner loop, so typically it takes about 1 millisecond from the sensor signal to the decision of the control. And we have a slow outer loop, so typically after 5 or 10 seconds, we know if the controller works or does not work. And then we test one controller after the other using genetic programming. And now we apply this technique to the Ahmed body, which I've shown earlier. Reynolds number is 300,000. So from an engineering point of view, we can reduce the drag by 22%, and our energy investment is about 3%. So we are distinctly positive. If we look how much time did we invest, we had our testing time was less than 1 hour in a wind tunnel. And at the end, we found that the best is unison blowing. So all 4 actuators follow the same controller, and the controller only listens to this sensor signal here. And I can explain why. Essentially, only this sensor signal can measure the high frequency feedback between actuation and sensing. Everything else would have a too high noise level. So what machine learning control did, first of all, it determined which actuator it needs to use. Secondly, it determines which sensor it needs to use. And thirdly, it finds the optimal controller. So success. What is the physics? The physics is, I'm showing here. Here we have some time average flows in the wake of the Ahmed body, which you see here. The unforced flow is shown here. So the yellow region is a backward facing, the backward directed flow. And on the right-hand side, we see the optimally forced flow. Looks pretty similar, it has a similar extent. But if you look closer, the wake is shaped in a boat-tailing manner, and this reduces the drag. Now, how did we learn this drag reduction? The next thing, what we do, we make a proximity map of the controllers. So this is an automated procedure. You put in the controllers, a metric, and then you get some gamma 1, gamma 2 associated with the controllers. If the controllers are similar, then they are close in this map. If they are different, then they are far away of this step, far away on this map. And here you see in the background, essentially the interpolated cost functions. Black means the drag is increased. The more white it becomes, the better for the drag. And you see a couple of maxima, you see a couple of minima, and at the end, you land in this corner. What is the explanation? Well, if we investigate the controllers, it turns out gamma 1 is correlated to the frequency. This is the highest possible frequency. Gamma 2 is correlated to the duty cycle. This is the smallest possible duty cycle. So we end in the corner with the highest duty cycle and the small, with the highest frequency and the smallest duty cycle possible by our actuator. So we see we are running into the limit of this actuation. If we could actuate with higher frequency or with even lower duty cycle, then we could have more drag reduction. So essentially, these proximity maps are very revealing. What we also learned that genetic programming is not particularly good in terms of exploitation. For instance, here we see we could land in a couple of local minima. Of course, it's not good, but if we start somewhere here, we should go quickly to this corner here. And this brings us to the next idea. Somehow we should use the gradient of the controllers. And this leads to the idea of the gradient-enriched machine learning control. Note that our search space is a Hilbert space. It's non-convex, has infinite dimension, has many minima, very nasty. And we want to solve this optimization problem, find the optimal controller, which minimizes the cost. And the first step, what we do a Monte Carlo random function set. So typically we take something like 100 individuals. So individuals are also are our controllers. And then we spread over the control landscape. In the next step, we do our genetic operations. So genetic operations are good for exploration to find other minima, and they are less good in finding exploitation, descending down to accelerate, essentially descending down these control landscapes. We include a downhill supplex. So we take the best individuals with the best cost. We make a linear combination of these controller, and then we do a simple downhill simplex method in order to descend down. So this is a basic idea. And we tested to another configuration, which we call fluidic pinball. So now this is a few years later, and we did not have the experiment anymore. The fluidic pinball consists of 3 cylinders. All cylinders can arbitrarily rotate. Now our flow sensors are now some U and V component in the wake, shown here. We want to make a controller. Using these sensor signals and driving the actuation commands, namely the cylinder rotations. 3 sensors, 9 actuators, laminar flow, 2-dimensional. Why are we excited about this configuration? Well, in principle, we can include all or the best, the most dominant drag reduction mechanism. In case of the Ahmed body, we have seen boat tailing, and we can emulate boat tailing by rotating the cylinders inward. So this way this makes the wake small. Another way of drag reduction may be base bleeding. So some fluid goes out of the inner cylinders. We can do that with the cylinders rotating in the other direction. We can also play a bit with the Magnus effect. This may be beneficial or not. Low frequency forcing has also been observed to be potentially drag reducing. High frequency forcing as well. In this case, we rotate the top and bottom cylinder in a symmetric way. And of course, we can also do some phasor controls, and so we use a sensor signal to always to stabilize the flow. And so now we leave it to our machine learning control to identify the best mechanism. And these are candidates which we know already from literature. So the goal which we have now, we want to stabilize the flow, want to be as close as possible to the steady solution. So this is the average distance to the steady solution. And we measure the actuation power here. The optimization problem is now to be as close to the steady solution as possible, and we monitor the actuation power on the side. So it's not penalized in this optimization. The first idea which comes to mind, if you don't know anything about machine learning control, so maybe we should expect a steady symmetric actuation to work. So bottom and top cylinders rotating in opposite direction, driven by one parameter. So this is one-dimensional optimization. And if we optimize that, then we get about 50% closer to the steady solution. And the drag power is 0.03. This is about 1% of the towing power. So it can be considered rather small. Next thing, what we do, we say, okay, let's take all cylinders rotating steadily. Maybe we gain something more from that. We would not expect it from a nominally 2-dimensional configuration, but we get it nevertheless. So in this case, we use an explorative gradient method to find the optimal parameters. Now we can go further to the steady solution. We are only about 28% away. The actuation power is about 4% of the towing power. And so we are better by enriching our state space. So this is what we would typically expect. And as a next step, we take the feedback controller and we use our optimizer, which was mentioned. And now we get 80% closer to the steady solution with a fraction of the towing power. So this is the best solution. And now the question, of course, is what did machine learning control find? What the other steady actuations were missing? If this video would work, you would see that the control would do a combination between phasor control and boat tailing. And I must say, in addition to the sensor signals, we also added the history of the sensor signals. And at the end, we get some asymmetric actuation. Here you see the vorticity field. And here you see the symmetric target solution, so we get reasonably close. Here you see the result of our gradient-based machine learning control. The cost one means we are on the limit cycle, on the natural dynamics. 0 means we are at the steady solution. Here you see our budget of 1,000 simulations. And the red curve represents the best results which we have achieved in one generation. So here is a testing of 100. Then we do 50 individuals genetic operation. You see that essentially the Monte Carlo only gives worse cost functions. And we need the simplex downhill search to get to better values. Then we again do some genetic operations, then downhill simplex, and so on and so on. At the end, we reach about 80%, the mentioned 80% cost reduction. If we compare this with standard genetic programming without these simplex steps, then with the same budget, we only get 37% cost reduction. And you can see we get these 37% already very early after about 200 individuals with a gradient-based machine learning control. So the gradient-based machine learning control significantly accelerates the search and also makes it better. Now the question, of course, is, would it work in an experiment? We have tried it with a open cavity plasma actuator. Here's a hot wire sensor. The goal is to stabilize the open cavity, and the stabilization is monitored by essentially the variance of the hot wire sensor here. A simple experiment. Here you see the configuration again. It's not a shallow, it's between a deep and a shallow cavity. It's about 1.5 times longer than deep. Reynolds number is about 10,000. It's an incompressible flow. And this is called bimodal non-intermittent regime. What you have, essentially, sometimes you have shedding with one frequency and sometimes you have shedding with another frequency. In this case, you see the velocity signal, but if you look at the spectrum, sometimes you see a Struer number of 1 and sometimes you need a Struer number of 1.3. So these can be explained with Rossiter-like modes. Plasma actuation essentially accelerates the flow near the leading edge. And if we just accelerate the flow without any dynamics, then we see the spectrum here. Without actuation, we get a beautiful peak at 1 and a small peak at 1.3. And the harder we actuate, the more we attenuate the flow. So the steady actuation now becomes our benchmark. What is our cost function? Our cost function is a variance of our hot wire signal divided by the variance of the unforced flow, and we penalize our voltage. So if we go to the breakdown voltage, that means that then this term becomes unity. And this penalization coefficient has been chosen also at unity. So this is a cost function which we penalize. We limit our observation to Struer number 0.5 and 1.72, so that we only have this, that we clearly have the dominant frequency in our monitor, and we optimize the controller. And again, we test the controller, we optimize the controller with 1,000 short experiments. What we get here, we get a cost function of 1%. So we have reduced the fluctuation energy by a factor 100. The actuation power is about 1% of the breakdown voltage. And there's another quantity, the variance of the hot wire signal, which also goes down. If we use with the same budget 1,000 individuals, standard genetic programming, then we are 4 times worse. And we also have a larger fluctuation energy. So clearly, gradient-based machine learning control outperforms genetic programming control in the experiment. And the feedback is really necessary, as we can infer from the spectrum. So, summarizing, machine learning control has learned multi-input, multi-output feedback laws for dozens of turbulence control experiments, always within a budget of something like 1,000 individuals. It has always matched or outperformed all existing feedback laws. We often found surprising frequency crosstalks and surprising spatial solutions, which were not reported in the literature. And when we put in the gradient-enriched variants, things only become better. We can explore the new minima with genetic programming, old efficiency, but we gain by doing the downhill Zaplex search. So as we have seen in the experiment, so in case of the fluidic pinball, we have found a combination of between bow-tailing and phasor control. In case of the optimal cavity stabilization, we have reduced the peak frequency by more than a factor 50. And we have a number of other experiments, which I cannot talk about, like successful robust drag reduction in Braunschweig and a 1 million airfoil lift increase now under time varying operating conditions. So these things are significantly harder than what we did before. What are the perspectives for the next EFAC seminars? So number one, we want to learn the reduced order model on the side. We think we have all the tools. We want to increase the learning speed by another factor 10, essentially using some of the models to guide it. And our next adventure is using something like 100 actuators, 100 sensors in the experiment, and optimizing about 100 geometric parameters, 100 controllers, driven by about 100 sensor signals from the same at the same time. And we also think we know how to do it. So if you want to know more, then you can about the fluidic pinball, then you can read some of the JFMs of Nandeng. If you want to learn more about machine learning control, you can consult the publication of Dikoneo Makeda, who will join us shortly as a postdoc here at HRT, or Hui Li, my PhD student. And we have also written a couple of review articles for machine learning for turbulence control. Thank you for your attention.
Yeah, thank you very much, Bernd. It's easy to say thank you. All the others have to use Zoom tools. There are already 2 questions in the chat. And Stefan, I think you will somehow get over. You will be the second. I would like to start with the other question. So Philippe Peitz asked, "Hi Bernd, I apologize for my ignorance. I don't understand how you obtain gradients in data-driven control without a mathematical model to take derivatives. Do you approximate via finite differences, or would it perhaps be reasonable to employ a derivative-free optimization method?" I think it's good if you start with this one, Bernd.
A very good question. So for this, I have to explain a bit the Zaplex method. So what the Zaplex method does, we start typically with 11 controllers, and then we explore the linear combinations of the controllers. And now we use a simplex method. The simplex method essentially does not need any gradients. So we reflect essentially in our low-dimensional parameter space and do a simple simplex method like with a few parameter optimization.
Thanks a lot, Bernd. If you want to discuss a bit, then please use the chat again. I'm sorry for that. That's due to the recording, so that's easier if we do it this way. So the next question is asked by Stefan Trenn. He said, "Your ansatz for the controller only considers static output feedback. However, in many situations, only dynamic output feedback can achieve the control objectives. Does your approach can be generalized to consider dynamic output feedback as well?
I do not know. So we take our sensor signals. Let's look at an example. One moment. So look at this controller. So we take the sensor signal and sometimes the history of the sensor signal. So here, so it's dynamic. So the actuation command is a function of time. It depends on the flow state. So this is a steady actuations which I have used. They were just to illustrate, to give our benchmarks, to show that the feedback component brings benefits to comparison with steady actuation.
Thank you, Bernd. The next question, Lars, you can ask directly.
I think so, yes. Thanks, Karl. Just a comment. I think what Stefan meant is dynamic, not in the sense whether it changes over time. Of course, the controller signal changes over time, but the question is whether dynamic information about the history of the signal is included in obtaining the control values. And I think you clarified that already on one of your slides that you do that. And I think this is...
Yes, the answer is yes. And there are multiple ways of doing that. So a brute force way is to take time-delayed signals. So you take time delay coordinate. And another possibility is you take filtered sensor signals. So what we also do is we take the sensor signal, then we take the short-term mean, we take the fluctuation, or we take certain frequency component, and then we let essentially machine learning control play. So most of our experiments, we include the time history of the sensor signal.
Then I think we thank Bernd again for this very, very nice and inspiring kickoff for today's seminar, and directly move on to the next speaker.
So our next speaker is Professor Jan Heiland, who graduated from the Technical University of Berlin in 2009. After this, he spent some time working for Bombardier Transportation before he started his PhD again at TU Berlin, which he completed in 2014. And since then, he has been a researcher and team leader at the Max Planck Institute for Dynamics of Complex Technical Systems. And in 2018, he was appointed junior professor at the Otto von Guericke University of Magdeburg. His research interests span a lot of different topics within systems and control theory, amongst others, robust control, differential algebraic equations, infinite dimensional systems, and model reduction. And the title of this talk today, as you can see, is Convolutional Autoencoders for Low-Dimensional Parameterizations of Navier-Stokes Flow. And I'm very excited to hear more about this.
I can't hear you, Jan. You have to unmute yourself.
All right, hello everyone. Once more, this sharing. Okay. Well, thanks a lot to Lassie for introduction, and thanks to the organizers for this great chance to present some very, very recent research efforts of our institute here. And this will be about convolutional autoencoders, so using neural networks, particular type. And we want them to help us finding very low dimensional parameterizations of Navier-Stokes flow. I will try to, I have an introduction, but let me go quickly first through a number of steps that should motivate what we are about. Actually, we are about finding very general approaches to solving nonlinear control problems. We come from linear theory. We like to solve Riccati equations, and we can have very large systems, and everything was very nice. There's LQG, which is a very general approach to that, but we want to do nonlinear control. And then there is this SDC representation of the control system. So it's the same system, but we have factorized this so that we have a matrix here that depends on the state. So the nonlinearity is not gone, but now it looks like a linear system. And here we have already some algorithms, well, that we like more because there's Riccati equations too. We will go further, and then instead of having AX, we will use a row of X, so a parameterization. And then we want to have a very particular representation, how the nonlinearity depends on this parameter that encodes the X in the system. And for that, we will use the neural networks. But let me start with introducing and some motivation and even a video. So this is the inverted triple pendulum that we have at our site in the Max Planck Institute. And we are able to swing this up with the model that I showed in a general form just on the slide before. And well, the parameters here is that it's a very nonlinear system. So we need a nonlinear controller for that. But it has only 9 degrees of freedom. So not many degrees of freedom. And well, and obviously we are able to run a computer algorithm so that the pendulum is controlled. Then this is another example that we like to consider a lot, the flow. We also saw it in Bernd's talk before. This in the wake, here we have a double cylinder. And this is a snapshot of a solution that you won't see in reality because it's an unstable state. You might see in reality if you apply control to it. And then in simulation, we can apply control and then we can observe this unstable steady state. And here the parameters is that the flow simulation has about 50,000 degrees of freedom. So a general nonlinear approach to that might already be difficult. But since we talk about stabilization, then we talk about small deviations, then we can use linear theory. But in fact, here we use a linear quadratic Gaussian regulator to control the flow as we want to have it. And the question that we try to answer here is whether we can have both. So can we have this very nonlinear systems, but also large scale? And well, we like these general approaches. And if we think of that, then there is a few items that possibly should be there. It should be in a form where we can apply our powerful computing backends. So linear algebra, we are very good in solving Riccati equations, for example, or even better if it were linear versions of that. So this should be somehow reflected. And also there might be optimization to be done. And this should also well be reflected in the system that we then use for the control. This goes also into exploitation of general structures of the model. Without any structure, it will be very difficult. And we try to put both together in finding surrogate models to that by using data that has a good structure that we can employ our linear algebra tools that we have for that. So in fact, in the end, we will basically combine all of that. Okay, and then so I will present these few steps how to get from this very nonlinear system, this general nonlinear system, towards a system that almost looks like a linear system, but with a parameter. But the first step is this SDC representation. Because under very mild conditions, if you do set point control, then your nonlinearity can be factorized in this form. There are many ways to this factorizations. There are good ones and there are not so good ones. But very general case, you can factorize it so that you now have x dot is a times x, linear systems as we like it, while with the little caveat that the a depends on the state. So for every x, we will have a different a. Well, and that's what it is. But also for this, there is theory, and well, to stay in the same class of system, one can of course think of a state-dependent control feedback law. So here this almost looks like an LQG feedback, but here the feedback, the gain matrix, the P, the Riccati solution depends on the state as well. And the basic approach for these systems, I would say, is using, in fact, the state-dependent Riccati equation. This goes back to many works by Banks and co-authors. Here, the feedback is said to be like the LQG feedback with the Riccati solution that is also part of the linear feedback laws, with the P being the solution to the Riccati equation. And in this case, since we talk about state-dependent systems, state-dependent coefficients, also the A matrix is state-dependent, and then we have to solve the state-dependent Riccati equation. And this means we have to solve a Riccati equation in every time step. And I said we want to solve large-scale systems, so this might be not the best idea. But still, there is theory for that, and it can be shown that under certain conditions, this nonlinear feedback law will be able to control the system towards an equilibrium. We did a little update on that, a slight improvement. basically we showed that instead of having to solve the Riccati equation in every step, and whenever the state changes, you have to solve a new Riccati equation, but you can get along with just solving a linear equation. And under a number of other conditions, basically on how the A behaves if the state changes, one can come up with the following algorithm that we have shown to be stabilizing under certain conditions. One has to solve the Riccati solution once for your starting state. And then as the state evolves, then of course the coefficient where we have it, the A matrix will evolve, will change. And then instead of solving the Riccati equation, one has to solve a linear version, so-called Sylvester equation, which is a linear equation. And here you can use your powerful linear algebra backends. Just make sure that this update is smaller than 1. If it's larger than 1, or there's a threshold still to the 1, then one has to do a reset. But we show that with the linear updating scheme, we can still have a stabilizing solution in the sense that we can control the system towards a steady state, towards a set point. Okay, now going further, instead of having x dot is ax times x plus bu, we require a special form of this state-dependent coefficient. And this is known as the LPV representation, linear parameter varying system. That's the LPV, linear parameter varying. And you can embed nonlinear systems in such LPV representations. If you have an SDC representation, then there is this trivial LPV. Just take the parameter rho to be the state itself. Then you see here, you see the SDC representation of the nonlinear system. But you can be better than that. Maybe you find a better parameterization that gives you a more structure to the A matrix. And what we look after is this affine linear parameterization, so that this A tilde of rho of x now looks like a constant matrix plus a sum of matrices, and then the parameter here is just a factor to these constant matrices. And this is a particular structure that has also been used before. The general topic here is controller design for scheduling. One considers the rho to be a parameter, and then one has to schedule the controllers accordingly. So typically there is a number of controllers available, and then you identify the regime, and then you take interpolants of the given controllers. And if you do this good, then you get a functioning nonlinear controller. And if you have this particular affine linear structure, there is, for example, very often cited work by Abkarian and co-authors, where they were scheduling H-infinity controllers to come up with a globally stabilizing controller that even had some additional robustness properties. And well, the basic information to that is that one needs to be the rho. So rho of x encodes the state, and one needs to have this rho confined in a bounded polygon. This is a basic assumption that is needed for that. And then if this controller exists, then it can be computed through solving K-coupled linear matrix equations, linear matrix inequalities. We like Riccati equation because we think LMIs is too difficult to solve. And now if they are coupled K times, then they get really large, and this might be out of size. So yeah, I will comment on this in a second. Because the other good structure that can be exploited of these linear parameter varying representation. So let me recall that now the A of x is a sum of matrices and multiplied with a scalar factor that depends on the x. If this is the case, then one can do a series expansion of the solution to the state-dependent Riccati equation, which means that instead of solving p of x for every x again, one has to solve a p0 for a p0, which is a Riccati equation solver, but that happens only once. And then one has to solve for these factors p alpha, and they are solutions to linear Lyapunov equations. So depending on how confident you are with this series expansion and truncating this at a certain step, then you may get along with just one Riccati solve and a certain number of linear solves, and update the controller according to this truncated series then. And here again, you see well, if this parameter k, oh no, I changed parameters here. So if the dimension of the parameters is small, then you are better off with the series expansion. If it's only one, then there is just the square, the cube, and the fourth power. And so if there's more than one parameter, then this multi-index kicks in, and there is very much different combinations possible until you have like a good series that well approximates the actual series. What to take of that is that if we have such a linear parameter varying system with this affine dependency on the parameters, then there are many opportunities to come up with general approaches for controller design. But it's really key that this dimension of the parameter is small. Yeah, and that's where we want to use the neural networks for. We want to design low-dimensional linear parameter varying representation. In fact, it's an approximation because we do an approximation in between 4 Navier-Stokes equations. And how do we get there? We use convolutional neural networks for that. Let me introduce the Navier-Stokes equations for a second. I'm not sure whether Bernd has it on the slides, maybe only in reduced versions. Here's a snapshot of such a cylinder wake, and this is a typical pattern you would observe if you do the simulation, or Bernd had pictures of experiments. There you also saw this the wake of a cylinder, for example, and these are the governing equations as we consider them. Most of you might know it. I just want to stress that here the nonlinearity in this equation, so this is a nonlinear system, and the nonlinearity is basically this convection part here, where there is the V times the nabla times the V, which is quadratic nonlinearity, we can call that. And there's not much to know for what follows about the Navier-Stokes equation. Maybe V is the velocity that describes the flow, P is the pressure, we will only work with the V, and the nonlinearity is in this particular quadratic form. Okay, because now if we have, say, a computed velocity solution, then we can find a POD basis to that. Well, did Bernd talk about POD this time? Not sure. So POD is a standard method to reduce nonlinear systems. What you do is you collect snapshots, information of the velocity. You take a number of snapshots, and then you do an SVD of the snapshots, and then you get the basis that you can express your velocities in with a very good accuracy, despite that you might only have a number of columns here in this so-called POD basis. And to put this in a formula, we will, with a good POD basis, the approximation of the velocity computed at time t is very well done with this product V transposed. This is the POD basis times the actual V, and this one, so this projected but then lifted again. This we will denote by the V tilde. And what comes out of here directly is that with this approach, the POD coordinates, as some people call it, they are such a parameterization of the velocity field, the POD parameterization. And this rho are then the so-called POD coordinates. But that's such a parameterization that can be used. And for the Navier-Stokes equations, because of this particular nonlinearity, this already defines what we are looking for: a low-dimensional linear parameter varying representation of the nonlinearity. In fact, if you, well, this was the approximated velocity that was once put down to POD coordinates to the low-dimensional space and then lifted up again to the original space, can be written as the POD matrix V times the POD coordinates times the rho, and this is the sum of the POD modes times the coordinates. And if we plug this into the nonlinearity, and if we use that this is a quadratic nonlinearity, so it's linear in both arguments, then we get such a linear dependent parameter varying system with a fine linear dependency on the parameters. So POD already might be a solution to what we look for, but we ask ourselves whether we can do better than POD. I must say POD is optimal, so it's known to be the optimal linear projection onto a low-dimensional subspace to encode the information. And the keyword here is the linear, so it's optimal as a linear projection. Maybe we can find a nonlinear projection that is better. We won't we won't contradict the optimality of POD, but we take a bit more efforts to have a nonlinear projection onto that. And we are motivated by some recent publications on model order reduction, where this is Karl and the co-author. They were looking at how to encode dynamical system information into reduced bases or in POD. You see here the POD, but also using deep learning approaches to find a so-called intrinsic nonlinear solution manifold. And what to take out of this plot is, if you look at the blue squares or at the magenta crosses, these are those two methods that included the deep. So they were using autoencoders for encoding the information. And here, what is the interesting region is here around the 3 and up to 10. So at the low dimensional, there's a clear advantage of the neural networks over just using a POD projection. And we have seen this also in another paper by this is by Choi and co-authors. Yeah, same picture here. NM means nonlinear manifold. There was a neural network to identify a nonlinear manifold. And here, in the interesting reason of the low reduced dimensions, it outperforms a simple, maybe not too simple, but this least square projection error using POD basis, for example. Okay, so we also thought about why not use autoencoders to that. And the approach of autoencoders based on convolutional neural networks here in just 4 steps. Ingredient is the data to that, and our data are snapshots of the solution that we have computed. And convolutional autoencoders, they derive from image processing. The idea is to extract features of the image first and then analyze it. So we first have to represent our snapshots as pictures. But I have shown you the pictures of the simulation, so this is like a natural way to represent information of the simulation. And then, from here, it's neural network magics. One has to learn convolutional kernels that extract these relevant features. During this extraction, dimensions are reduced. So if you concentrate on the features, you might not need all this pixel information anymore. That's what's happening here. And then in the final step, we will encode what we get out of these convolutions into a low-dimensional parameterization. I made a little sketch of what this looks like on our computer. Here to the very left, you see we start with the pictures of the simulation results interpolated as pictures. Then there are these convolutional layers that reduce the size but also extract features. And here the third dimension that you see, this is the feature channels, meaning if you have 4 of them, then there are like 4 channels where you can store features. And during this process, you reduce the size more and more, but you increase the features that you might store. Then at the last step, before the actual encoding, there is a standard full linear layer with an activation function that then should return this low-dimensional parameterization. And somewhat special in our approach, instead of going backwards to this convolutional network again to get to a representation of the velocity again, we try to learn improved POD coordinates. So we expand this row a bit to have more coordinates, and those we will use as POD coordinates to restore the solution again. And the trick here is that in this last layer, we won't use an activation function, so we will have a linear relation of the actual encoding to this expanded encoding. So if we later write down our nonlinear system with this code or with this parameterization, then we preserve any linear affine relation because of this linear relation between the actual encoding and the expanded encoding. Here, just the information once more. Important to that are the inputs. Here we use velocity snapshots of our FEM finite element simulation that were 50,000 degrees of freedom, and we interpolated them. That's just a very blunt interpolation. There's upcoming projects with doing a bit more sophisticated stuff here. But we interpolate this to pictures two pictures. We have two velocity components, and then this makes such a three-dimensional tensor as the input to the neural network. Other important question is how to do the training, what to train the network for. Here it's just recovering the data after it has been encoded in this very low dimensional row. And here the trick is that we use still the POD mode to recover the velocity, but well, the goal is here getting this row as small as possible, because this means that there is a parameterizing the velocities of a very low dimension. Another important feature here is that we include the FEM code, at least in this case through the mass matrix, because the norm is important that we are in the right FEM norm where we do this optimization. What we would like to do is adding more physical information for that. And this would look like, instead of just recovering the data, we would like to recover the how the advection term is affected by that. So instead of putting the velocity as the advection velocity, we would like to put the reduced velocity, the reduced parameterized velocity here. This will give us directly the linear parameter varying representation that we want. Still, we are not there because here we really have to include FEM operations. You see here this dual norm we have to realize somehow, but also these differential operators should be included here. This is not so easy to be included in a standard neural network package because of the backward mode that should be preserved all the time. Right here, I'm almost done. Let me show what we got out of here. I'll show you what was the setup in a second. And important is here we are in the very low dimensional regime. Here we only have 3 dimensions for the encoding. And here we can beat the POD by a factor by about 50%. We are still better here. It's not a large margin, but if you think that POD is optimal in a sense, then this certainly is an improvement. And we are here in the dimension that's important. And what you also see that if you go larger, here we are at 12, then POD is already better. Quickly, what were the simulation parameters? It was this wind awake at Reynolds number 40 on a time interval from 0 to 8. We took 1,000 data points, and we had this convolutional neural networks with 4 layers. And these are some parameters of the how we designed the network and the training. All right, let me just conclude. I tried to convince you that linear parameter varying representations of nonlinear systems with these affine linear dependencies are attractive for controller design, but we need a small dimension of the parameterization. Here I've shown that one can use the CNN to improve the POD at the very low dimensions that are of interest. Next thing would be to include the parameterized convection in the training so that you train what you're really looking for. And then finally, we hope we can use this for general approaches to nonlinear control design. That's it from my side. Thank you. And here's the references.
Thank you very much, Jan, for that very nice talk. I think we have a question from Bernd, if you want to take it live, or a comment.
Yeah, I think it's a very exciting framework, and you're addressing the key issues. One question with respect to the manifolds. I'm not so sure that if you use POD modes, that this is a good choice. Because you take a transient cylinder wake, and suddenly you need 50 POD modes to capture the whole transient because the structures are always changing. And at the end, everything lives on a 2-dimensional manifold. And you can uncover the 2-dimensional manifold on a couple of other approaches like isomap, local linear embedding, feature-based manifold, and so on. This is just mentioning for transient data, POD may not be a good pre-compression, even if you try to modify the coordinates afterwards.
Okay, good point. So we try to find this nonlinear manifold without your engineering or physical insight?
Well, this is neither engineering or physical. This is computer science. If you do local linear embedding, it's a key-press solution. You don't need any. You just put in your snapshot data in metric, and then you can figure out what does a 1-dimensional parameterization, a 2-dimensional parameterization, and so on give you.
Thanks. Yeah.
Okay, another question. In how far can frequency crosstalk be embedded in your framework? I see that in theory it could. So, you know, frequency crosstalk is maybe you actuate at one frequency and you order to mitigate another frequency. And so in theory, what you have presented, it should be included. I'm not so sure if it would work in practice.
We haven't looked for that. Certainly, because we look for nonlinear relations. So the model is inside what we look for. Maybe an idea that we have on that is also trying to use maybe space-time blobs. So trying to connect the space and the time in the data in the training, and then this might be even a better chance to get these transitions from one frequency to another. But good point. So
there's one thing, a smooth transition in time, and another thing is essentially having one frequency component, maybe of the interaction of the actuation affecting the other frequency component of the flow. So typically it happens by using the Reynolds stress, changing the mean flow, and the mean flow changes, makes maybe an unstable frequency suddenly stable, or the other way around.
Yeah, maybe also something one could like put in the model directly before training.
Okay. I have many more questions, but I will stop now.
So maybe I'll take a very brief question here that we've received from the audience. So there's a question here from Jonathan Ayala Leon, who mentions in the beginning of your presentation with the pendulum, you said there were only 9 degrees of freedom. I'm not sure if you mean 9 degrees of freedom is good or not. Would it be better to have more degrees of freedom for this system?
No, it's working. So we already used the minimal coordinates for that. So we try to get as low as possible. Like this model worked good for us. I didn't judge the number there. I just think that here we have that many numbers for the model, and we can come up with a computer with a controller that works on the computer. Maybe there are better models for that. Yes.
Okay, perfect. Thank you. So I think there is a question also from the audience, but because of the recordings, I guess we should take it in the Q&A. Tim?
I guess in the interest of time, we have to move on. So please, if you have any questions, type them in using the Q&A functionality, which helps us to stay on schedule here. And I think we thank Jan again for this very nice talk, and directly move on to our next speaker, which will be introduced by Karl.
Yes, thank you, Tim, for handing over. Thanks, Jan, for giving your talk. I enjoyed it very much. And now it's time to move on. So we move on to Professor Matthias Müller from the Institute of Automatic Control of the Leibniz University Hanover, Germany. Matthias received a diploma degree in engineering cybernetics and a Master of Science in electrical and computer engineering, the latter from the University of Illinois at Urbana-Champaign in the US. In 2014, he obtained his PhD in mechanical engineering from the University of Stuttgart, Germany, for which he also received the 2015 European PhD Award on Control of Complex and Heterogeneous Systems. And this nicely fits to the fact that Matthias is actually dealing with application in different fields, including biomedical engineering. There are some other things I really want to mention. So last year, he received an ERC starting grant, and also was one of the 2 recipients of the inaugural Rocket Williams Outstanding Paper Award for the best paper published in System and Control Letters in the period of 2014 to 2018. The other recipient will also give a talk today, so that's our pleasure. And yeah, Matthias recently added to his research quite a bit on data-driven control, which also received a lot of attention, I would say. I guess the respective award will follow in due course. And I think that we get some insight on the underlying ideas during today's talk entitled 3 Perspectives on Data-Based Optimal Control. So please, Matthias, the stage is yours.
Yeah, thanks, Karl, for this very nice introduction. I want to thank Tim and Karl and also to Lassi for putting together this very nice workshop and also for inviting me to present some of our recent research. So this is joint work with Mohammad Asalti, Marco Nonhoff, who are PhD students, and Victor Lopez, a postdoc in my group in Hanover, and then Julian Berberich and Frank Allgöber from Stuttgart, and Johannes Köhler, who is now a postdoc at ETH in Zurich. So I have to admit, when I submitted my title and the abstract to Tim and Karl, I mistakenly assumed that I would have 45 minutes of time instead of 30 only. So this is why I might only tell you 2 perspectives instead of the announced 3 today. Let's see how we progress in time. I guess in the end it will be 2.5 most likely. So this is the outline. I want to first start without giving too much of a motivation, because it's a seminar on data-driven control, right? Why I do data-driven control, but directly move on to the data-driven system representation, which I will be using throughout the talk. And then, yeah, consider 3 particular optimal control problems, right? First, just a standard LQR problem, where we devise an off-policy Q-learning algorithm, and then move on to online convex optimization, and finally, if time allows, also to model predictive control. All right, so what's the data-based system representation which I will be using here? So consider a linear time invariant system G, right? And assume you can collect input and output data denoted here by UD and YD, right? And the question is, can we use this input and output data which we collected in order to describe the underlying system G without identifying explicitly the ABCD matrices, right? So can we find a purely data-based system description for this unknown linear time invariant system? And to this end, we will exploit a result which recently has gained quite some attention again, which was originally published by Jan Willems and co-authors in Systems and Control Letters in 2005, so roughly 15 years back. So let me highlight a couple words from the abstract, right? So they say that they show that if a component of the response signal of a controllable LTI system is persistently exciting, then windows of this signal span the full system behavior. Right, so I will make this more precise on the next slide, but basically the idea is collect some persistently exciting data, and then you can use this for describing the complete behavior of your unknown underlying system. Right, so first, what means good or informative data, right? Just U not equal to 0, U not constant. Well, the notion which we need is persistency of excitation, and this we define in terms of this Henkel matrix here, right? So if we have an input sequence of length capital M in total, right, then the Henkel matrix of depth capital N contains windows of length n of this input sequence, right? So U0 to Un minus 1 in the first column and so on. And then we say that the signal is persistently exciting of an order n if this Henkel matrix has full row rank, right? So if the rank of this matrix is M input dimension times n the number of block rows here. All right, and then basically this fundamental result by Jan Willems and co-authors says that if we have a linear time invariant system of order n, which is controllable, and if we apply to this a persistently exciting input of order n, so capital N will be the length of the sequence and plus small n system dimension, and collect the corresponding output data, then any input-output trajectory of sequence pair of length capital N is a trajectory of the system if and only if this equation holds. So there exists an alpha such this equation holds, meaning that I can write this input-output pair as a linear combination of the columns of that Henkel matrix. Right? So meaning that these Henkel matrices span all possible trajectories of the system, or put differently, any possible input-output trajectory of the system is a linear combination of windows, so of time shifts of this persistently exciting input-output sequence, which I collected a priori. And this is a purely data-driven system description. So very briefly, right, I think the if part of this result by Willems is quite easy to see, right? So linear combinations by linearity and time invariance, linear combinations of trajectories are trajectories again. The only if requires the persistency of excitation, and very loosely speaking, right, it requires order capital N, length of the sequence, to be able to reproduce any possible length n input sequence and then plus small n, so very loosely speaking, to be able to reproduce any initial condition of the underlying unknown system. And one more remark, persistency of excitation of order capital N plus small n at least requires this number of data points to be collected a priori. All right, so to sum up this first part, so using a single open loop data trajectory, which is the input is persistently exciting, we can describe all possible trajectories of an unknown linear system via this equation here. And in the following, I will show you how we can actually exploit this in order to obtain data-based solutions to 3 different optimal control problems. The first one being linear quadratic regulation, the second one online convex optimization, and the third one, again, if time allows, MPC. All right, so let's go into the first main section of my talk. And here, as I mentioned, the problem we consider is the simple, maybe one of the simplest optimal control problems, right, the LQR problem. So here the cost function clearly is to minimize this infinite horizon quadratic cost function. For simplicity, we assume positive definite weighting matrices here. And in this part, we assume state measurements to be available, right? So we can measure the state and not only some output, but the system matrices A and B are assumed to be unknown. All right, so let me first define the value function and then also the Q, the quality function, before then proceeding with specifying the Q-learning algorithm. Right, so just the value function when using a specific input all the time. So U equals minus kx is denoted by vk, and that's just evaluating this quadratic cost functional when applying this input. On the other hand, the Q function is defined for a state and input pair, and basically it's the one-step cost, right? When being at the current state xt and when using this input ut, and from then on using U equals minus kx for all future times from time t plus 1. Right, so this Q function evaluates the cost of using an arbitrary input ut at time t, and then using U equals minus kx for all future times. All right, so now given that we have a linear system, right, so we can express that, so this is basically a quadratic form here, this value function, then we can express the whole thing as just Z transpose times some suitably defined matrix theta k times Z, where Z is just a stacked X and U vector here. And this theta k matrix is a positive definite matrix. Now, one more remark, which will be important for the Q-learning algorithm is that, right, it's easy to see that if I evaluate the Q function at U equals minus kx, then I just obtain the value function vk. Right, and so if I basically, the equation here, basic definition of the Q function with vk replaced by qk of x and minus kx, this will appear later on when we define our algorithm. All right, now if we have, let's say, a certain control policy and know the corresponding Q function, right, then what we can do is, and that's how most of the Q-learning algorithms actually work, right, we can define an improved policy by minimizing the Q function with respect to U. Right, and this clearly yields an improved policy such that Q mu, if we apply mu, is less or equal than Qk if we apply minus kx. Right, and now as I showed on the previous slide, right, the Q function is just this quadratic form in Z. So here it's clear if we just take the gradient with respect to U, set it to 0, then it's easy to see that this is the optimal solution here, right, where these matrices are just the respective partitions of that matrix theta k. All right, now given these preliminaries, we can now define our proposed data-based, any Q-learning algorithm is data-based in some sense, right? But using Wilhelm's lemma, so we can now define an off-policy Q-learning algorithm, and it actually works as follows. Right, so first, offline, we collect persistently excited data, right? So we apply some persistently exciting input and measure the corresponding system state. Second, we need to initialize our algorithm with a stabilizing feedback matrix. I will comment on that later, briefly, how to do that. And then this is the core part, right? We solve for the Q function at the ith iterate of the algorithm, right? So we solve for the matrix theta I by solving eta of these equations here, which are composed using the a priori collected data. And if you recall, this is nothing basically but the definition of the Q function, so which all the data has to satisfy, right? So this is just the Q function at iteration I, right? Evaluated at a point Z, X and U, which is just by definition X transpose QX plus U transpose RU, and then plus, remember, plus the value function at the next time step, which is equal to the Q function evaluated at minus kx at the next time instant. And that's nothing what we have here. Right, so this theta is just xt plus 1 and minus ki, so the current ith iterate of our policy times xt plus 1. And now the key actually, and that's the main technical part, which takes some work, is actually to show, and I will comment on that briefly later, that under suitable conditions, this set of equations has a unique solution, theta I, for which we can solve. Now, once we have solved that, we can just update our feedback policy matrix. So the next iterate is then just given as I showed on the previous slide, and we do just that until we have converged to a certain tolerance. Right, so the main idea of this and of all Q-learning algorithms is basically that, right, if we have a policy, right, we evaluate it, compute the corresponding Q function, and from this find an improved policy. Now, where does Willems lemma or this database system representation come into play here? Right, so first I want to mention that we at least need to obtain this number of samples here, right, where n again was the system dimension and m was the input dimension. And then that's what I mentioned before. This is the main part, right, of our proof. By Willems lemma, it's easy to see that this matrix here has actually full rank, and this matrix contains these z vectors, right, as columns. So we have, since it has full rank, so we have n plus m linearly independent columns. And if in addition none of these vectors is a multiple of another, then we can actually show that this allows to uniquely identify or compute this matrix theta I at each iteration. Now, this is not really a restriction. If this should be the case from the previously collected data, we just collect some more data and delete those rows basically where we have, which are multiples of another. So that's not really a restriction. So that's the idea behind it. And so what are the theoretical properties which we can show for this? So again, as I said, if the data is persistently exciting of order n plus 1, and if none of these a priori collected data vectors are multiples of each other, plus we have this initial stabilizing matrix, which I will comment on in a minute, then we have the desirable properties that any iteration yields a stabilizing matrix. As I goes to infinity, this matrix converges to the optimal LQR gain K star, and moreover, we have a quadratic rate of convergence. So this equation here holds with a gamma, which is independent of the system dimension. So let me quickly illustrate this first part by comparing it with one of the other. I mean, in recent years, right, there have been quite some other database design techniques for the LQR problem being proposed. So let me compare it to one of the recent results by this group by De Persis and Tesi, which also used Willems lemma, but in a different context, and in the end obtained some LMIs to solve this problem. And so here we compare both the average error, right? So KF is the final result which the algorithm gives. So our algorithm, the Q-learning, stopped after 10 iterations. For each dimension, 10 iterations, and the LMI we were using just solving CVX with the default settings, and also the average runtime. So we sampled randomly 100 systems of this dimension, of these dimensions here, and then here we report the average error and the average runtime. And as you can see, so the method already after 10 iterations is very exact, and yeah, the exactness is much better actually than for the LMI approach, and also the average runtime is actually scales much better with the system dimension. So we have also some theoretical investigations about that, which I'm going to show here. All right, so what are the main features, or as a summary of that first part, right? So we can guarantee stability and convergence to the optimal LQR policy under some rather mild, I would say, persistency of excitation conditions. Compared to other existing Q-learning algorithms, I think the main distinctive feature is that this is an off-policy Q-learning algorithm. So we need to compute or collect persistency exciting data only once. And these intermediate iterates are never applied during learning as in on-policy algorithms. Also, it has a rather low computational complexity and a fast rate of convergence compared to other existing database methods. And I mean, maybe the main caveat is that we need an initial stabilizing matrix for our unknown system, right? Which might be difficult to find, but there are actually also some recently proposed methods, for example, by the Groningen group, how you can actually compute, for example, a deadbeat controller very efficiently, also without solving complicated LMIs, so that this really is also negligible in time if you do the comparison there. And also we have some results. So what I only showed you was for noiseless data, but if you basically have noisy data collected a priori, then you can still show that actually if you just run the algorithm more or less the same way on the noisy data, then it still works, and you get, of course, you cannot retrieve the perfect LQR gain, but you converge in a neighborhood of the optimal LQR gain. All right, so this was the first part on data-based Q-learning for LQR. Now let me move on to online convex optimization. So what is this actually? So let me motivate that, or say, what this control problem is. So here we're looking at a finite horizon cost function, right? So we sum over some potentially large constant t, some time varying cost, LT of u, right, subject to some constraints. And these cost functions are a priori unknown, right? So I know the past cost functions, but I don't know the future cost functions. So this actually, this type of problem, and notes that actually this is a static problem in the sense that there is no underlying dynamical system, right, as formulated here. Now in this form, that problem actually has been studied in the machine learning community in the recent, I would say, 10 to 15 years very extensively, and many different algorithms and variants have been proposed to that end. One of the simplest solutions there is to use online gradient descent, meaning that what the solution there is, at each time you just choose the previous input, ut minus 1, plus a step in the negative gradient direction of the previous cost function, right, which you know. And then basically you do just one step here, right, and then the environment reveals the cost function LT, which then leads to the cost LT of this u which you applied. And then you just repeat this. Now this has actually been successfully applied to a variety of applications where always some terms of the cost function, the performance criterion you want to minimize is actually a priori unknown, or you have some unknown and unmeasurable disturbances, like in economic dispatch and power system, data center scheduling, electric vehicle charging, peak shaving in electricity nets, and so on, where either like electricity prices, the arriving jobs in a data center, or the loads or whatever, the renewables are unpredictable before. And so the advantages is actually that this is very computationally very efficient, right? You do just in this very simplest form, just one gradient step online. So you don't explicitly solve the complete optimization problem online. You can handle time varying and unknown cost functions. I will discuss later what a good performance metric is in that setting, right? Which is the notion of regret. And also that you can have state or constraint satisfaction. Now, our group and also others have very recently, in the last 2-3 years, I would say, studied how you can actually extend that if there is a dynamical system underlying. And today I want to show you very recent results where not only we have a dynamical system which is underlying, but also where the system is unknown as well. So that we have a priori unknown cost functions and also unknown ABCD system matrices. Right, and again, we will be using Wilhelm's lemma, this database system representation, to this end. Now, very briefly as notation, right, so the minimizers of these a priori unknown cost functions are denoted by theta and eta, and we need the assumption that these are actually strongly convex functions. You can also relax that, I think, to convexity only, but this is the assumption which we in any case need. Now, what is the algorithm we're proposing for that end? Which online convex optimization algorithms for unknown linear systems? So the first step is, so let me quickly walk you through that. The first step is that we do basically compute an estimate V of eta using online gradient descent, just in the input dimension. Second step is that we compute a mu step ahead prediction of the output, and this mu is kind of a prediction horizon which needs to be at least as large as the controllability index of the system, so at most dimension of the system, right? And how we do that, I don't want to go into detail here, but basically here you can see that actually these Henkel matrices appear again. So here we use Wilhelm's lemma, and basically this is simulating the system in a database fashion, right? So we fix the initial condition. We fix an initial condition of the underlying unknown system by fixing basically the past n inputs and outputs to be equal to the real observed inputs and outputs. And then basically the simulated input is a suitably adapted version of the previous optimal input. And then just the simulation is again also done by suitable rows of that Henkel matrix, so which is basically a database simulation of our output. And then here we do a gradient descent step, right? So we compute now a desired set point, again using online gradient descent in the output dimension, right? And in addition, so this is basically here what we do here, and also compute a corresponding set point, again in a database fashion, right? So this SU and SY matrices again depend on these Henkel matrices of the previously collected data. All right, and then what we need to do is modify our input sequence such that actually we really end up at this new desired set point after mu steps. And again, without going into details, this can be done in database fashion using Wilhelm's lemma. And this optimization problem can explicitly be solved offline using weighted pseudo-inverse matrices. So again, not an optimization problem which we need to solve online. So we keep the computational efficiency by just having 2 gradient evaluations and various matrix vector multiplications online. And then we just apply the first part, and then we repeat the procedure. All right, so this is basically the main idea of the algorithm. Now, what is actually the theoretical properties we can show for it? So first, the performance metric, which is meaningful here, is this notion of dynamic regret, which compares the performance of our online algorithm to the optimal trajectory in hindsight, which is the optimal trajectory if I had known beforehand all the cost functions, right? And what we can show is that this is basically the result we get. So I'll interpret that on the next slide, but let me first say the assumptions, right? If we have a persistently exciting input again, we need a prediction horizon, which is, as I mentioned, larger than this controllability index of the system. We have two more assumptions, which are maybe a little bit more restrictive. The first one is that we have tracking type of cost functions, right? So that this minima of these cost functions are all steady states of the system. So if you're familiar with MPC, for example, no economic cost functions, right? So this is one of the current research issues. And also an assumption which may or may not be restrictive depending on the application, but this is what is needed currently in the algorithm as well, is that we actually, for each output y, there must exist an input such that this pair is a steady state. So there are matrix rank conditions, sufficient conditions for this, and this requires that we have at least as many inputs as outputs. All right, so these are the assumptions, and this is the result. Now, what does this actually mean? So first of all, these constants, importantly, are independent, of course, of this horizon t over which we evaluate the performance. And basically the regret, so how much the deviation to the optimal trajectory in hindsight is upper bounded in terms of this term here, which is a measure for the variation of the cost functions, of the a priori unknown cost functions, right? So if these do not change much, then we have a low regret. Of course, if they change randomly, then of course also the regret will be larger. And also as a corollary from this, it directly follows that if the cost function should be constant after some time, then the closed loop converges to the optimal steady state. All right, so what is current work here? So, so far we only have theoretical results for perfect data, which is maybe not the most practically relevant case, admittedly, right? But in simulations, it works very nicely, actually, also for noisy measurements and noisy a priori collected data. So that's what Marco is currently working on. Also that we can use more general cost functions and also to add constraints. Constraints can be solved actually in one of our recent works in a model-based but state feedback setting. And so we're trying also to currently to incorporate this in this data-based output feedback setting. All right, so now I think I took already 22 minutes, so I don't have much time for the third part, but let me at least give you the main idea without going too much into detail. And this is MPC, right? So I think I can skip, since it's a workshop on optimal control. I guess you all know what MPC is, so I can go over that slides without discussing it really. And this is the data-based MPC problem formulation, which we're using, right? So again, this is, I would say, a standard MPC problem for linear system, right, with constraints. And the difference now is that instead of a model, we use this data-based implicit model of the system, right? And also, similarly to what we've seen before, this here fixes an initial condition of the unknown underlying system, right? So we say that the first n components of the predicted inputs and outputs have to be equal to the past n observed input and output measurements, right? So that's, and then as usual in MPC, you solve this to optimality or suboptimally if you want, then you apply the first part of the optimal control sequence and then you repeat everything again. So what I mentioned, different to many of the existing MPC schemes, this is inherently an output feedback MPC scheme. It's model-free, and the complexity also, without going too much into detail, at least if you take the minimum number of data points, is comparable to model-based MPC. Now, yeah, so this actually, we were not the first ones to come up with this scheme. So the first, I think the basic idea was brought forward in this paper by Young and Lee 2015, and also a group, Florian Dörfler, John Lugeros from ETH, did some very nice extensions and reformulations of that, and also applications in 2019. But actually, there were no stability proofs and robustness proofs available. And this was what we have been developing in the last 2 years. So I think I can skip the motivating example why this is of relevance, because it can be unstable without if you don't choose the horizon properly. And so one easy remedy is similar, borrowed from model-based MPC, to use some terminal constraints. And the terminal constraints is now again a constraint on the input and outputs to be the same for n consecutive measurements. And with this and with perfect data, actually, the stability proof goes through rather straightforwardly. The only additional challenge compared to the model-based case is that we do not have positive definite, but only semi-definite cost functions because we only penalize the output and not the state. It gets much more interesting if we do have inexact measurements, which is always the case in practical applications, right? So, and now we assume that we have actually output measurement noise both in the a priori collected data and also in the online data. And there, actually, we need quite some modifications and a much more, I would say, involved proof to be taken. But I think the main idea is also quite intuitive, right? So what we do is we introduce slack variables to render the equation feasible, right? Because now here we have disturbed data, right? We add an additional slack variable here to make this equation feasible. And then we do additional regularization of both the slack variable and also of this parameter alpha here in the cost function, right? So the MPC problem now looks as follows. All the red terms are new compared to the nominal case, right? Here we use a two-norm regularization of both alpha and sigma, and also this slack variable here. If you want, in a sense, on a high level, this is similar to model-based MPC with both parametric uncertainty and additive output disturbances, right? Why parametric uncertainty? Because we have uncertainty here in the model, so in the Hankel matrices. All right, and now then again under suitable assumptions. So if we have persistently exciting data, these regularization parameters are chosen suitably. So I don't go in detail here, but we have we have lower and upper bounds, how to tune them, and also if the noise bound is sufficiently small. And additionally, if we use a suitable constraint tightening, which I don't show here, but we have some results how to do that in a data-based fashion again. So again, without knowing the system matrices, then we can actually show robust constraint satisfaction, practical exponential stability of the closed-loop system. And interestingly, I think the region of attraction increases and the tracking error decreases if either the noise bound decreases or the minimum singular value of the input matrix of the previously applied, so this persistently exciting input increases, or the data length M increases. So in a sense, if the persistency of excitation to noise ratio gets better, right, then we can also get, as expected, better theoretical results. All right, so I guess I also skipped the application where we just show it in a 4-tank example that it actually works nicely. Yeah, and with that, I'm at the end. I want to conclude. So what I have shown you today is that using a suitable system representation in data-based fashion, which was originally proposed by Jan Willems, we can actually exploit that for different optimal control problems, as I've shown in this talk, for an efficient off-policy Q-learning algorithm for linear quadratic regulation, for online convex optimization, for dynamical systems with both time-varying unknown a priori cost functions and unknown system dynamics, and also for MPC with stability and robustness guarantees. So there's actually a multitude of future research issues, for example, less conservative stability, robustness conditions, external process disturbances, or in some, this is somehow solved, at least partially in some of the approaches, and others not yet, and so on. But it's very open and also very active field of research. Not only we, but also others are working on that. Is some first approaches for nonlinear systems. So everything only was for linear systems, what I showed you today. For example, we have some recent extensions of Willems' lemma to flat nonlinear systems, and also some first guarantees for nonlinear MPC based on locally linearized models, where we actually update the data in the Hankel matrices online. And with this, I again want to acknowledge, so the first part was mainly Victor's work, Victor Lopez, a postdoc in my group on the Q-learning. The second part was mainly Marco Nonhoff's work, a PhD student here in Hanover. And the third part on MPC was mainly Julian's work, a PhD student in Stuttgart. And with this, I want to thank you all for your attention.
Yeah, thank you very much, Matthias, for the very nice talk. We have a lot of questions, actually, and I start with Eric's first question. What is the difference between Q-learning algorithm and the standard dynamic programming recursion? If they are the same, in brackets, which they seem to be, are you finding that dynamic programming recursion is more efficient than solving the equivalent single-shot LMI?
Yes, it's of course very related. I mean, also, yeah, and I mean, also in the context of approximate dynamic programming, right, there's much literature in that respect. Yeah, I mean, I think as far as I know, at least in the machine learning literature, right, often these policy iteration algorithms firm under the name Q-learning. And yeah, so I mean, in that particular example, which we found here, or actually in these results we had, that this is more efficient, yes, than at least, I mean, I cannot say then for any LMI-based iterations, right, or algorithms, right, but for that, for one of these, I would say currently up-to-date and existing data-based control design methods using LMIs, it's more efficient, yes. Not sure, does this answer your question, or you cannot really reply, but.
Tim, maybe you can unmute Eric if that's fine for him. And in between, we have another question, I would say, due to technical issues otherwise. So Levin Ökreme is asking, in Q-learning, mostly a discount factor is used so that the definition of the value function and action value function would change. Is there a specific reason why it is not considered here?
Yeah, that's also a very good question. Yes, I agree that often in Q-learning you do use actually discount factor here. I mean, here we were interested in the standard LQR problem where we use non-discounted cost functions. Yes, but of course, I mean, the things and the equations and so would change if we do use a discount factor. Yeah, we did not study that here because we wanted here to study the standard LQR problem. But yes, so things would change, but could also be done, I think, in a similar way. With, of course, suitable adaptations, so not trivially maybe, but in a similar spirit.
Okay, so far I don't see Eric.
I think Eric is unmuted. He can talk now.
Yeah, I'm unmuted. Yeah, can you hear me? Yep. Okay. Thanks, Matthias. Nice talk. Yeah, so it does appear that it's a dynamic programming recursion, right? So my follow-up question, which I did post, which they didn't read, was, if it's faster than setting up these LMIs, why is the dynamic programming recursion faster? Is it just because you're working with smaller matrices, whereas maybe in the LMI approach, they're forming these bigger and bigger matrices? I don't know, right? I've not read, De Passis and Tesi's paper in detail to really look at the computational issues, right?
Yeah, so I hope I don't say something wrong. So if I recall it correctly, I would need also to look in the details of our work. But I think, yeah, we're using smaller matrices in one case. And so I think it scales with the order. I think it scales both polynomially in the system dimension, but I think it's somehow in the order, if you really do the comparison of all the steps, I think it scales polynomially to the power of 6 or 7 in the LMI case. And to the power of 3 or 4 in our case. So it's both polynomial. So there's no difference there, but the exponent is smaller if you do the computation.
Yeah. Okay. That probably makes sense. Maybe not, right? But thanks. Yeah.
Okay. Then we continue with Stefan's question. Stefan wrote, concerning the optimal control with unknown cost function. Isn't that mathematically an ill-posed problem? Shouldn't there be some assumption that the future is correlated to the past to arrive at any meaningful heuristic method?
Yeah, I mean, of course, I mean, in order that this online gradient descent makes sense, right? Of course, it only makes really sense to go in the direction of the previous cost function if, let's say, the next cost function is not completely different, right? I mean, that's captured in this regret bound here. Of course, if the cost functions change arbitrarily, right, then also this is basically the change of each of the cost functions of the optimizers of the cost functions, right? And of course, if this is very large and they change completely in an unpredictable behavior, then of course going in the direction of the previous cost function also intuitively does not make sense. I totally agree. So I think this somehow is, I mean, always, I think some underlying assumption is that, let's say, at least it's a good estimate and cost functions don't change too fast, let's say. And then of course this is captured here in the fact that then this right-hand side of that bound would be small. But yeah, I agree with your statement, yes. And but I mean that's often the case. I mean, depending on the application, right? If let's say you have some unknown parts in the cost function, some prices, some loads, often, let's say in some applications, right, this makes perfect sense. Or let's say arriving jobs at the data center, or let's say the queuing in the queue, then what you have there in these applications, which I mentioned there, typically, I mean, these are some assumptions which do make sense there. But of course, in other applications, this might not be the case.
Yeah, thank you. I think 2 more questions before the coffee break starts. So Bernd is going first, then Lars.
So you're doing some data-driven control, and then how far or what do you have to assume about your control landscape, about your dynamic system, so that your methods work? For instance, if you do the online gradient descent, I would assume you assume something like that. Suboptimal control should work. That means it's a next stack optimization of the control should lead you in the direction of your cost function. And I assume also that you assume that you are not stuck in local minima or something like that.
Yeah, so yes, thanks for the question. Yeah, so I mean, I think the first part of the question goes in a similar direction as Stefan's question also, right? I mean, only taking one gradient step brings you in a meaningful direction, right? If the cost functions do not change arbitrarily from time to time. And second question, yeah, I totally agree. And I mean, we assume convexity, right? So we don't treat non-convex problems. So it's typically all this framework on online convex optimization considers convex cost functions. And then, of course, it's nice. And of course, if you have non-convex cost functions, then the world is different.
With non-convex would be, for instance, if you have noise, then you can have if you have saturation and a couple of noise, then you have non-convex situation.
Well, yeah, I mean, the situation, I mean, the cost function as such should be convex, of course. I mean, if you have noisy data, right, I mean, yeah, but I mean, then, of course, you don't get perfect convergence to the optimum in any case. But still, I mean, you would get practical convergence in that setting. Or I'm not sure whether I understood your question correctly, but...
I mean, that means at the moment you have a dynamical system plus noise.
Yeah.
At this moment, the noise can be very counterproductive to these algorithms. So you don't have any smoothing or any simplification in your algorithms.
Yeah, of course. I mean, it in any case deteriorates the problem. Yes, that's completely correct. Yeah, and I mean, including maybe some filtering would be helpful, I guess, in that case. But I mean, we still get converged, let's say, to a neighborhood, and of course, the size of the neighborhood scales, of course, with the noise. This is that's the results that we have.
Yeah. Okay, thank you.
Thanks, Matthias. Lars, please.
Yeah, I have a quick practical questions because I implemented actually some of the ideas you presented in the course of a master's course I gave in the last couple of weeks. And I found out that depending on how you choose the persistency exciting UD, so this internal, external U that you need for cracking, you can get very ill-conditioned matrices. Is there a systematic way to avoid this, or was I just unlucky, or maybe not clever enough? Do you know about that?
You mean that the data matrices are very ill-conditioned?
The data matrices not really, but the KKT matrices, for example, for the optimal control problem you solve in each step of the MPC scheme.
Ah, okay. No, I have to admit, I haven't encountered that, so I cannot really say something meaningful at that point. Sorry.
Maybe we can discuss offline too.
Yeah,
you can
very interesting.
Explain to me what you used, or maybe it's written somewhere in your paper. I don't know.
Thanks. Yeah, I would say in the interest of time and in the interest of our coffee break, let's thank Matthias once again. And yeah. Tim, if you agree, we make a coffee break and we start nevertheless at 4.
I think we build in some slack, so I would suggest we start at 4 p.m. European summertime, and see you then. Enjoy the coffee break.
So our next talk is going to be by Professor Lars Grüne, who has been professor for applied mathematics at the University of Bayreuth since 2002. He got his diploma and PhD in mathematics in 94 and 96 from the University of Augsburg, and his habilitation from the Goethe University in Frankfurt in 2001. Since then, he's had multiple visiting positions in Rome, Padua, Melbourne, Paris, Newcastle. So it's been many exciting places. In addition to this, he's editor-in-chief of the journal Mathematics of Control Signals and Systems, and associate editor for several other journals, including the Journal of Optimization Theory and Applications, Mathematical Control and Research, Control in Related Fields, and the IEEE Control Systems Letters. His research interests lie in mathematical systems and control theory, with a particular focus on numerical and optimization-based methods for nonlinear systems. And his talk today, titled A Deep Neural Network Approach for Computing Lyapunov Functions, will touch upon some of his work. And I'm very excited to hear about this, so please, Lars.
Yeah, thank you very much to Lassi. Thanks for the very kind introduction. And my talk will be quite different from the talk that we had before, because I will really look at, instead of looking at all these challenging real-world problems, I will look at a actually quite simple model problem. Jan Heiland in his talk mentioned something about neural network magic. And I think my task, at least my intention, is to take a little bit of the magic out of the neural networks and try to explain why they work so well for some problems and what kind of problems this could be. The problem class that I'm looking at is this computation of Lyapunov functions. And before I start, let me give a little commercial break. I'm from Bayreuth, and maybe most of you do not know where Bayreuth is or how it looks like. You have the chance to figure out. I hope that by next year, September, we will be able to have the conference MTNS 2022 in the classical form, at least more or less, so with people in person on site. And I would very much like to welcome you if you are interested to this very nice conference series, which takes place in my university. Okay, here's the outline of the talk. Back to the research program. I will briefly talk about Lyapunov function and about deep neural networks. I'm not sure how many people in the audience know about these deep neural networks. So far, no one really explained how they work, and I will take a few minutes to do that in my talk. I will then talk about complexity analysis for this problem that I'm looking at, what this has to do with small game theory that some of you may know from nonlinear control. Shortly about training algorithms, and have some numerical examples in the end where I may have to rush through a little bit, but okay, anyway, we'll see how time works out in the end. Yeah, so first part is about Lyapunov functions. What is this? You may have heard about these in courses on ordinary differential equations. That's what I'm looking at here. I have an ordinary differential equation in Rn, x dot equals f of x, and we have some initial condition x naught. We assume that 0 is an equilibrium, so that means that f of 0 is 0. And then a continuous differentiable function is called the Lyapunov functions if there are 3 k-infinity functions such that the function itself is bounded from below by one of these, where we plug the norm of x in, bounded by above by another of these, and the derivative in the direction of the vector field is bounded by minus such a k-infinity function. Now, k-infinity function, in case you do not know, is a function which maps the non-negative reals into the non-negative reals. 0 at 0, strictly increasing unbounded. So this is the graph you should have in mind if you think of a k-infinity function, right? And they appear 3 times in this definition of a Lyapunov function. Yeah. Just a very simple example, mathematical pendulum with friction here. So we have this friction term, which means that it's asymptotically stable. So the swinging gets slower and slower until it almost stops at the downhanging position. This is how it looks in the x1, x2 plane. So this is the position, this is the velocity. We get these spirals which spiral into the origin, and the Lyapunov function could, for example, be this expression here. And if you then project the solution of the ODE onto the Lyapunov function, it looks like this. It's nicer to see if I turn it a little bit like that. And here you see that the Lyapunov function actually decreases along the trajectory. This is this third condition. And eventually the solution ends up at the global minimum of the Lyapunov function. That's the whole issue with Lyapunov function, the whole trick about that. Yeah, what are they good for? Why should we compute these kind of functions? Well, first of all, they provide a certificate for asymptotic stability, which is nice. You can estimate the domain of attraction of a asymptotically stable equilibrium via the level sets of Lyapunov function. You get information about robustness, so you get some information about how much you can perturb the vector field f such that you still get asymptotic stability. In case of control Lyapunov functions, about which I will not talk, but to which some of these results could be extended, it's actually possible to design stabilizing feedback laws from them. And this is probably in this context here of this optimal control technical committee, the most interesting aspect. It's actually a quite simplified model problem for a more general Hamilton-Jacobi-Bellman equation, because actually Lyapunov functions are characterized by equations which are a very simple class of Hamilton-Jacobi-Bellman equation. And this, of course, has motivated a lot of research for the numerical computation of Lyapunov functions. There are series expansion methods in the literature which use what I call Zuboff type equation. This is precisely the Hamilton-Jacobi-Bellman equation I was mentioning. So it's this kind of first order PDE or transformation thereof, and these are used in these schemes. There are finite elements for this equation. There are finite elements combined with linear programming. It's a very interesting approach by Sigi Hafstein, developed during the last 20 years. There's sum of squares methods, of course. There is radial basis function approach, so mesh-free methods by Peter Giesel and co-authors. And what all of them have in common, these methods, is that they use some kind of gridding of the state space or of the parameter space, where the computational effort grows exponentially in the space dimension n of the ordinary differential equation. So if we have an ordinary differential equation in dimension, say, 2, 3, 5, 2, 3, 4, 5, it can work, can or cannot work. If we go beyond, it gets really, really difficult to solve them. This is the notorious curse of dimensionality, a term coined by Richard Bellman, as far as I know, which is apparent for all classes of Bellman equations, Hamilton-Jacobi-Bellman equations, and so on. Yeah, and I think that for general ODEs, this is probably not a bad estimate, but simply just unavoidable, because the complexity of such a Lyapunov function can really grow. These things can, from dimension to dimension, they can become more and more complicated because solutions can twist around, make strange moves. And in the general case, I do not think that we can overcome the curse of dimensionality, but it may be possible that under suitable assumptions on the ODE, there are Lyapunov functions which have in some sense a simpler low-dimensional structure, and they can then be represented with much less effort. And this is the question of this talk, that how can we, I would like to present one way to detect and to exploit such structures. Yeah. Neural networks for Lyapunov functions are not a new topic, so I have to mention previous work. Many of these is actually for control Lyapunov functions. Here's a list of papers, probably not complete. And what is different in my talk here is that all these algorithms, they present training algorithms, so they are very practically oriented, but they do not necessarily provide a complexity analysis. Actually, I think none of them really does a rigorous complexity analysis, and this is really the distinctive contribution of this talk here. Okay, I would like to use deep neural networks, and what is this? Well, this is the class of deep neural networks I'm going to use. So we have the input, which is just a state vector. Then we have at most two hidden layers here of neurons, and then we have the output, and the output is actually the approximation of our Lyapunov functions, and theta is the vector of parameters. I would like to be a bit more concrete here. What do we have? So we have the input values here, and these are processed via the activation function sigma 1. So we get this wk1 times x. This is a scalar product here. So w is a vector of weights. Dot is the scalar product. We plug the x in here. We add b as a scalar parameter. We apply the activation function here, which is a function from R to R. And then we get the values of all these neurons here on the first hidden layer. An activation function, well, we've seen some of them already or heard the names. Here are some simple examples. Linear activation function is something I will use. This is called ReLU, rectifying linear unit, very popular. And this is a smooth version of this one, which turns out to be more suitable for the application that I have in mind. Yeah, and then from the first layer to the second layer, we do basically the same. The only thing that changes is the index. So everything gets an index 2 now. And instead of the x, we have the y1. So the values of these neurons here. So we get a new set of vectors, of weights, scalar parameters, and so on, and activation functions. And in the end, the w is just a linear combination plus this bias term here of the second layer. And this theta is the vector of all the parameters, and this w is then what should approximate the Lyapunov function if we have chosen our parameters theta star in an appropriate way, so for the trained network. So that's the idea. Okay, that was the setting. And now let's come to the main part of this talk, the complexity analysis, and what this has to do with the small game theory. Yeah, so some of you may have heard about the universal approximation theorem. This is for a class of functions which looks like that. This is not really important what exactly that is. It's basically a class of functions where the partial derivatives up to a certain order m are bounded here by a constant and which live on a compact set. And the important thing is this theorem, which was developed over several years in different versions. This is the version I got from a paper, from a survey paper that appeared a few years ago. And it says that if we have a hidden network with a neural network with one hidden layer, and sigma 1 is infinitely differentiable and not a polynomial, then for any epsilon greater than 0, there exists such a network, if I just take enough neurons in this one hidden layer, such that we can approximate any of these functions G from this set with an accuracy epsilon in the L infinity norm, if we take the right theta, which of course depends on G, right? And we can also give an estimate of the minimal number of neurons that is needed, which is of the order of epsilon to the power of minus n over m. M is the m from here, so this is the regularity of the function, and n is the dimension here, right? The state dimension. And what we get from that is that arbitrarily good approximation is possible with a single hidden layer, but the effort that you need in terms of the number of neurons again grows exponentially in the dimension n. So if you make n larger and larger, you will see this exponential growth of this number, which is here if you keep epsilon and m fixed. So this grows again exponentially fast, which is, well, not what we would like to have, because this means if we use a neural network for the approximation of Lyapunov functions, in the general case, we face exactly the same issues as for the grid-based method, complexity-wise. Okay, but there's always a good question whether you should use a catchy title for your paper. In this case, it worked out because this paper caught my attention a couple of years ago. And it says, when can deep but not shallow networks avoid the curse of dimensionality? And the key idea that is laid out there, which is of course not new because it's a survey paper, which was developed before. The key idea is actually absolutely simple, and many of you may have heard about that already. It says that if the function g that we want to approximate is of so-called compositional form, which means it's a nested composition of certain functions g1, g2, g3, and so on, which depend on a number of arguments m, which is small and particularly independent of n, right? So here we have two arguments in here, one argument in here, two in here, two in this, actually two now in this g1 function, and so on. Then the number of neurons that we need does not grow exponentially with that. And the reason is quite simple, because you basically can build a network which has sublayers which represent these component functions here. And since these component functions are low dimensional, the number of neurons does not grow if the dimension grows, not exponentially in these sublayers. Only the number of sublayers grows, and this number only grows polynomially. So that's the key idea, which is actually very simple, but of course needs to be made precise in a function analytic way. And very particular simple examples are so-called separable functions, which are functions which are just sums of functions which depend only on parts of the components of the vector x. And these parts I combine into these vectors zj here, right? And the number of components in each zj should again be is again noted by m, at most m, of course, and they should be bounded independently of n. The number of subsystems is at most n, right? And for Lyapunov functions, this is precisely the form that we get from so-called nonlinear small game theory. So let me spend 3 slides to explaining what that is. What we do is we decompose not only the vector into the subvectors, this is z1, z2, and so on, up to zs, but we only decompose the f on the right-hand side of our differential equation in the same fashion, so with the same dimension, and then we denote all the z which are not contained in zi as z minus I. right? So this is then Z1 up to Zi minus 1. Then we continue with Zi plus 1 and go up to Zs, right? And then with a little abuse of notation, we can actually write the overall system as a system of smaller subsystems of the form Zi dot equals Fi of Zi and Z minus I, right? And these are S subsystems at most N of these. And if we are very, very lucky, we can do this in a way such that these systems completely decouple, which means that each Fi does not depend on Z minus I, but only on Zi, right? So that we have this identity here. And in that case, it's very, very easily seen that if we compute Lyapunov functions for the individual F1 to Fs, right? So we compute for all the low-dimensional subsystems, we compute Lyapunov functions. We can just add them together, and the result will be a Lyapunov function for the overall system. So for completely decoupled system, we get automatically a bundle of low-dimensional subproblems, which is much easier to solve. But unfortunately, this is, of course, a very, very rare event. And if a system is really a system, then it should be connected in some way. So interesting dynamical systems represented by ODEs are hardly ever decoupled. But small gain theory generalizes this idea to something which is not necessarily decoupled. And this works as follows. So now we have this coupling. Now Fi may depend on the other components, on the Z minus I. And we assume that we have Lyapunov functions of the following form for each Fi. Well, if you just think that this sigma is not there, which would happen if Z minus I is equal to 0, then we have the usual Lyapunov function inequality up to here. But now this negative term here may be perturbed by a positive term, which depends on how large the other states are, right? Lyapunov functions always look like these bowls, right? So if Zj is 0, we have 0, but if Zj becomes large, we get something positive. And this gamma ij is again a k-infinity function with so-called ISS gain, which amplifies this Vj, well, more or less, depending on what this gamma ij actually is. And this is has to do with input to state stability theory, and so this is called an ISS, input to state stability Lyapunov function. Actually, we have S of them. And if the gamma ij are sufficiently small, and this does not mean that any of these is sufficiently small, but well, they all together in a suitable way, which I do not have the time to fully explain, but I would like to point you to these very nice papers on this theory, which appeared about 10 years ago. So if they are sufficiently small, then we can actually define these auxiliary functions vi hat. And these vi hat, they actually then, if we sum them up, are a Lyapunov function for the overall system, right? And here are a couple of papers where this is done. So these were the first papers which considered only 2 subsystems, and I think Björn Rüffer was the first to generalize this to many subsystems in the form we need it now. And this particular result is from this paper of Sergei Dashkovsky, Hiroshi Ito, and Fabian from 10 years ago. Okay, and this is now precisely the form which is a separable Lyapunov function, and this is very good for being approximated with a neural network. Yeah, the trouble is that the most difficult part in small gain theory is to determine the appropriate subsystem structure. So which are how to build these vectors Zi. And this structure may even be hidden. So maybe we have to do some transformation before we can do this. And nice thing is that, of course, in a neural network, you can do this very easily by just adding another network layer. And I have limited myself here to a linear layer, which determines or which represents a linear coordinate transformation that can help to determine the subsystem structure that we need in order to get an efficient representation. So the proposed network architecture is the following. We have the input here. We have a first hidden layer with linear activation functions, which is just a coordinate transformation of this of the input. And then the second layer has these sub-networks, which represent the different vi hat that I showed you, and approximate these. And then by just adding them up, we get to the Lyapunov function v. And the theorem then says, all Lyapunov functions which are of this separable form, even with a coordinate transformation, which is allowed here, Ti, or actually S coordinate transformations, T1 up to Ts, which just have to satisfy a rank condition in order to make sure that the dimension of the subsystems is not too large. And this Dmax is independent of the overall dimension. They can be approximated with an accuracy epsilon, with a number of neurons growing only polynomially in D. And I think I now, by putting together slides, I jumped in the notation. D is the dimension which was N before. I think I made a copy and paste error here, so apologize for that. So D is what was N before, and the max was also called M before, right? But otherwise, it's all the same. And the nice thing now is that the small gain theory, which is a beautiful theory, but very hard to apply in practice usually, is not, you do not need to know all these functions which are in there. You do not even need to know what Zi is. The hope is that if we know that the structure is there, but do not know where it sits and how exactly it can be represented, then the training algorithm will hopefully figure out by itself what is the structure. So the network will learn the structure during the training process. Yeah, so let's talk a little bit about how we can train the network to do this. Yeah, the basic thing is that we always need a loss function, right, in order to train a network. This tells the optimization algorithm what is the error that should be made small. We need a data set here. I just need randomly chosen points in the set K where I want to do the Lyapunov function. Then we minimize this weighted sum of the average of the loss function for all the points. And what is a bit unusual here compared to other learning approaches is that we not only have W as an argument of L, but also the derivative of W, which we of course need because a Lyapunov function is characterized by a condition on its derivative. Yeah, and the choice of the loss function that I'm using here is inspired by recent papers on solving PDEs using neural networks. Here's just a short list of papers. This is exploding this field. So, and they basically use all similar training algorithms. And we know that Lyapunov functions satisfy this Zuboff equation, so this very simple Hamilton-Jacobi-Bellman equation. Actually, for the examples that I have, it's always fine to use this minus x squared here. And we have this, what I could call boundary conditions, this upper and lower bound on V. And we can represent the violation of these three equalities and inequalities via this loss function here, which penalizes with this term the deviation from this equality, with this term the deviation or the violation of this inequality, and with this term the violation of this inequality. So here we take the negative and the positive part so that we only penalize the deviation in one direction, right, to capture this inequalities here. Now that sounds nice, but there is an issue with that, and the potential issue is that there is a nice theorem from the 1960s that says that a solution V of the Zuboff PDE always exists if the boundary conditions are chosen appropriately. But this solution of this PDE may not be of compositional form. So even if a compositional Lyapunov function exists, this may not be a solution of the PDE. It may be something completely different. So possibly it doesn't make sense to really enforce this PDE, and it may be more efficient to use the partial differential inequality, which is actually all we need for a Lyapunov function, again with the boundary conditions. So we should maybe also try the loss function, which only penalizes the deviation of this, or penalizes this term in one direction. So only if this inequality is violated, but if dv is less or equal than minus, much smaller, there's no penalization. Right? So this is what this term here does. Okay, let me finish with a few examples, and I think I have 5 minutes left to show them, which is nice. The numerical settings were as follows. As I told you, the first layer just represents the coordinate transformation, so I use linear activation functions. For the second layer, soft plus turned out to be very good, and I more or less picked them because I thought, well, that looks like a reasonable function as an activation function for a Lyapunov function. In the meantime, we have made some experiments in a master thesis, which shows that actually they perform better than most other activation functions in this application. So by chance, I picked a real good choice, it seems, when I did this. In each sublayer, we have 128 neurons in this network. The implementation was with TensorFlow in Python, which I think is the standard these days. The optimization was done using the Adam optimizer, readily just taken from TensorFlow, which is one of these stochastic gradient methods. The computation was always done on -1 to the power of n. And the optimization was terminated when in all test points that we had, in all data points, the violation of the loss function was less than 10 to the -6. So this is the L-infinity norm of the loss function, if you wish, over the whole data set. So it's really a quite strict termination criteria. Yeah, let me start with something very simple, a two-dimensional example. This is the ODE I'm looking at. It's actually quite easy to construct a Lyapunov function by hand, which is obviously of the compositional form. So we have one term which only depends on x1, and additively a second term which only depends on x2. I start with this second loss function I presented on a network with two sublayers. The dimension was limited to 1, so I'm explicitly looking for a Lyapunov function which consists of two one-dimensional additive functions here. This gives me a network with 775 trainable parameters, and I use 200,000 test points in order to do the computation. And then this is what we get. The solid is the Lyapunov function. This grid here is or this mesh is the derivative times f. And we see that it nicely does what it should. So the Lyapunov function is positive definite. It has this k-infinity lower bound and an upper bound. And the derivative has this negative k-infinity upper bound. So it's exactly what we want to have. Training took 48 seconds, which is absolutely not competitive compared with grid-based methods, but okay, it's a first try, right? I tried the same example with the equality-based loss function, which really tries to enforce the Zuboff type equation. And interestingly, this failed to produce a satisfactory result. So no convergence, and what we get after this non-convergence looks like that. Not too bad, but if you look closely, you'll see that the minimum is at the wrong place and that actually the derivative becomes positive in certain points. So this is not really what we want. It's definitely not a Lyapunov function what we get. Yeah, then I thought, okay, this is a theory that says it should work also in higher dimensions. So let's try something which is a bit more challenging, not terribly, but at least 10D is far beyond what we can do with grid-based methods, right? Far beyond. And also, in order to check whether this coordinate transformation idea works, I took a vector field which actually has, which satisfies the small gain conditions, which you can see if you look at this splitting up here. These are actually 5 two-dimensional systems which are coupled, but coupled in a way that the small gain condition is satisfied because the coupling strength is small here. And then I took a coordinate transformation, randomly picked, and transformated this so that you cannot really see anymore where this subsystem structure sits. And yeah, the training was done with a network that looked actually for two-dimensional sublayers and used 400,000 test points. This is just a cut, right? This is now, of course, a 10-dimensional space, but this is the function in the x2, x8 plane when all the other coordinates were set to 0, and it looks very nicely. And also, if you turn it, you see that it's actually really a positive definite function, negative definite derivative, and they touch exactly in 0, which is what they should do. Computation time is now very competitive, 266 seconds. It's really something that you can hardly get for a 10-dimensional example with any other method I know of. And this is also another sanity check that this is something reasonable. I just computed the solution of the ODE numerically and evaluated the computed function along the solution. This is a nice, strictly decreasing function. For different initial values, it always looks the same. It looks just like it should. So it seems that this works very reasonably. also in at least moderately high dimensions. Okay, with that, I'm done. Let me conclude. So it is possible to use deep neural networks for computing Lyapunov functions. And if the Lyapunov function has a nice structure, in this case a compositional or separable structure, then it's actually provably possible to overcome the curse of dimensionality. And this is certainly just the beginning, but already now with this very ad hoc setting, we can handle dimensions that are far beyond those that are feasible for grid-based methods. And small gain theory, in a sense, justifies the whole approach because this is a theory that describes situations in which compositional Lyapunov functions actually exist. And I have several questions for future work, but one is that, we can, it looks all very good, but we have no proof that what we get is really a true Lyapunov function. And I'm also not really aware of an efficient method that we could use to check how good our solution is. Right? It looks good, it does everything, but is it really a Lyapunov function or something which is very close to a Lyapunov function? So we need some verification tools that would be very nice to have. And the second is that we would like to generalize the whole thing to optimal control, to general Hamilton-Jacobi-Bellman equations, that in the sense that we then use value functions instead of just simple Lyapunov functions. And this will be a project in a priority research program that will start in Germany in fall. And we will work in this project for 3 years on that topic. And hopefully, as I learned from Bernd's talk, is we need material for future IFAC seminars, and hopefully something good will come out such that I will have the possibility to talk on some of the future events about our results from that project. Here are 3 references. This is the main paper, which just appeared in the Journal of Computational Dynamics. There's also an archive version. This is an earlier conference version of the same thing. And this is already a couple of years old, but nevertheless, very interesting review on other computational methods for Lyapunov functions, in case you would like to learn about that. Yeah, with that, I'm done, and thank you very much for your attention.
Thank you very much, Lars, for that very nice talk. So I see that we actually have quite a few questions, so we'll do as many of them as we can, and maybe you can answer the rest offline.
Yes, I will do that.
Perfect, thank you. So I'll start with a question by Matthias K. Hoffman here. So he writes, I understand the idea of the linear layer, but how does it actually help? The second layer activation function input is then an affine function of an affine function, which is affine in itself. Shouldn't this composed affine function be learnable as the weights and bias of just the second layer?
Very good question. I thought myself about this for quite a while, and I think it's not the case, because the affine function that we need inside the activation function, these are the degrees of freedom that we need for the approximation, for approximating the function. And the only thing we can do with that is basically exchange, right? So we could say, instead of saying Zi are the first 10 components and Z2 are the second 2, we could shuffle them around. But we cannot really, I think, do a full coordinate transformation with that. With that, we use up the degrees of freedom, and then we do not have the degrees of freedom left, as far as I think, to really do the approximation in these layers. But I'm not fully convinced. Maybe there's more to that, and maybe this is overly complicated. I cannot exclude that, but I thought a little bit, and I think it would not work. But of course, it would be worth a try. Yeah, good question.
Okay, thank you. I see also that there is a question. There is a hand up in the panelists, so maybe we can take that live if
sure.
Bernd, if you.
I sympathize very much to essentially tame the curse of dimensionality using a Lyapunov function. I think it's a very promising path. I'm not so convinced that actually, if you have a high-dimensional system, Lyapunov function can be constructed in the way you've presented. Let's assume the following thing: you have something like a spiral.
Yes.
Where you go downwards. So essentially, if the direction of the descent kind of changes. So if the manifold is strongly on which the effective dynamics is strongly curved, at this moment, even you can show that a Lyapunov function cannot be constructed. So I wonder, where do you expect your approach to be typically applicable, and where do you expect it not to be applicable?
Yeah, very good. You're absolutely right. If you have this spiral, you cannot decompose this into two one-dimensional. This is exactly the situation where the small game theory does not work, right? But where I expect, well, I mean, actually, I would like to go for control problems. And in control, there are many techniques that construct control Lyapunov functions, like backstepping, forwarding. This was all very popular in the 1990s. And at a certain point, it got stuck because it's computationally very demanding to do all these constructions analytically then. But what this theory gives you are indeed control Lyapunov functions which have a compositional structure, because they are built up recursively by adding more and more coordinates, right? So they have this in a natural way. And this is precisely the situation where I hope that this can work even in high dimensions, where we have this structure. And we know quite well how the vector field has to look in order to apply this technique. So this is one example where I think it can work. And indeed, you are right. If you have something where everything is intertwined and everything interacts strongly with everything else, this will not work, definitely. But my hope is that there are many interesting, and also from the application, interesting examples which have some low dimensional structure which we can exploit here.
Thank you.
Okay, thank you very much. So maybe we can take one more of the questions from the Q&A. So we have a question here from Stefan Trenn, which is, after training the network, how do you verify you actually found a Lyapunov function, i.e. that it satisfies the conditions for all x?
Yeah. Definitely. I think he posed the question before I came to my conclusion slide, because this was exactly the first question. I don't really know. There are techniques. So Chris Kellett and a co-worker has a paper where they propose some verification techniques, but whether these techniques would work in higher dimensions, I'm not really sure. So we have to look at that, and it's a very good point. It's an open question at the moment. So and it's an important question. I absolutely agree. Yeah.
Okay, thank you very much. I think in the interest of time, maybe we finish the live questions here, but there are many very interesting questions in the.
I can just answer them offline. I think I should do it before the session ends, right? Because otherwise everything will.
Yeah, if possible.
I'll try to do this well during or after the next talk. Okay.
Perfect. Thank you very much for the very, very nice talk.
Thanks, Lars, for the talk. And we directly move on to the last speaker for this seminar today, which will be Sebastian Peitz from the University of Paderborn. And Sebastian is indeed a perfect example of the, let's say, interdisciplinarity of data-driven control, because he has done his bachelor's and master's, if I'm not mistaken, in mechanical engineering at RWTH Aachen, then moved on pursuing a PhD in applied maths at the University of Paderborn, and just earlier this year joined the computer science department in Paderborn. And I'm very curious to hear Sebastian's thoughts on the universal transformation of data-driven models to control systems. Sebastian, the stage is yours.
Yes, thank you very much for the introduction, and also for the opportunity to present my work here. I would like to talk a little bit about model-based control, and more specifically on how we can use surrogate models in a universal way to solve optimal control problems, and also model predictive control problems for highly complex systems where models may be available, but may be much too expensive. And what I'm going to present is joint work with Katharina Bika, who is also located in Paderborn. But before I start, I would like to give a short motivation why I think that such a universal approach may be helpful. So the systems I'm thinking about are usually governed by complex dynamics. Let's say we have aerodynamic systems or internal body flows, like on the right side, breathing, maybe an example. Or you have these high-dimensional agent-based systems like pedestrian simulations and so on. So there's a ton of examples where we have a large number of degrees of freedom. And if models are even available, which may not always be the case, then numeric simulations are usually very, very costly. So this is a challenge for optimization and control. And what people usually do, and have been doing for several decades now, is to accelerate this evaluation using surrogate models. And more recently, the data-driven perspective has gained more and more attention, obviously. Well, and the idea or the issue that I see in data-driven modeling is that if you consider control inputs, then this modeling part often becomes more difficult, more data hungry, and it may also be highly problem specific, which makes this a complicated task that has to be repeated if you change the system or maybe the boundary conditions in your PDE and so on. So this is why I think that a universal way to incorporate surrogate models into control systems may be helpful. And this is what I will be talking about. Before I do so, I will give a quick introduction into the notation and also into surrogate modeling, in particular in the context of control. And then I will spend quite some time on discussing how do we guarantee errors or error bounds for such systems, which is, I think, quite crucial if you think about real applications in, let's say, security relevant systems like autonomous driving and so on. So what I would like to solve is this very general optimal control problem where I have an objective functional J, which depends on the state Y of a system that is described by a differential equation. So what I have here is Y dot equals G of Y and U. So it's an ODE in this case because Y only depends on time, but this may also be the discretization of a PDE, for instance, or you could also pose this as a PDE constraint problem, but let's stick with ODEs for now, which this also makes the error analysis a bit more easy. And this is now a continuous time problem, so we're looking for a control function from time t0 to the final time te. And what a very common approach is, and also which is much more suited to data sets, is a discrete version of this problem. And we can simply achieve this by setting u of t constant over a time grid, so between ti and ti plus 1. And this then gives us this problem number 1 in the bottom, which is the discrete time version of the one above, and we have the dynamics are encoded in this capital phi, which is now the time t map from time step ti to ti plus 1. And this is the expensive part in my system. So I want to evaluate this, or I need to evaluate this phi many times. And this is expensive, and this is the reason why I want to replace this phi by some surrogate model. And as I said in the beginning, this is highly popular, and there's a tons of literature on this, POD, for example, or other methods. There's really quite a lot. And the general idea of this is to replace the dynamics for my system state Y by a reduced order model phi r for some surrogate state zi. And the relation between the full state Y and the reduced state Z is by this function f, the observable, which may be, well, it might be the full state observations, so Z and Y are identical. We may have partial observations, pointwise measurements, projections on the subspaces, nonlinear functions of the state, and so on. So this is rather arbitrary and depends quite a lot on the surrogate modeling technique and the system you're looking at. But this has been done for very different settings over and over again. And what the problem is that in the control setting, this becomes more challenging. I already said this in the introduction, and the reason is that for one, the surrogate the model dimension usually increases, and due to this also the data requirements. For example, if you think about neural networks, then you have the issue that you need to consider the control input, the network layer number increases, or the number of neurons and so on. Or if you use these quite popular state augmentation approaches where you treat the control input as an additional state, and then you have again an autonomous system, then the dimension increases obviously, and so does the data requirements. And the second large challenge, from my point of view at least, is that the modeling may be very problem specific. So there are ideas, for example, the Koopman operator has been really popular in the dynamic systems literature recently, which is a linear operator describing the dynamics of this observable function f that I introduced on the slide before. So you need to exploit this linearity, for example. This is tailored then to the specific surrogate modeling approach. Or in POD, for example, you need to modify the data that goes into the surrogate modeling process. For instance, in the case of POD, to have homogeneous boundary conditions of your data set, because otherwise the Galerkin basis you create using POD may violate the PDE boundary condition and so on. So this is quite tedious and obviously depends on the very specific boundary conditions of your setup. So these make all these problems quite more challenging than in the autonomous case, which I think is more advanced at this point at least. For several methods like the Koopman operator or neural networks like LSTMs or reservoir computers or stochastic modeling approaches and so on, there has been work. I think the papers are appearing on a daily basis on surrogate modeling using these methods and others. And the important part for my discussion now is that for many of these approaches, there even exist convergence results or error bounds. So for POD, for example, there's this famous paper by Kunisch and Worthmann from 20 years ago, where they show that you have a bounded error in your prediction. For the Koopman operator, there are similar approaches in the infinite data limit, but also more recently for finite dimensional data sets or finitely many data measurements. And you have similar results for linear systems and so on. So the question that I would like to ask before going on is, if we want to use this in a universal way, and if the modeling of autonomous systems is so much more advanced, then instead of constructing surrogate models for the control system, why can we not adapt the control problem to our modeling approach and just pick our favorite modeling methodology? And well, I wouldn't ask this question here if I don't think I have an answer to this. And the approach that I would like to suggest is to quantize the control. So if we have a control set U, let's say for simplicity, these box constraints between U min and U max, then we can replace this by a finite dimensional set V, which may only consist of the control bounds, let's say. So just the two entries U min and U max. And this now allows us to replace this continuous control program that I had on the first slide by this version where we replace the set U by the set V, and which makes the right-hand side not a non-autonomous system, but a finite set of autonomous systems depending on which U I pick. And I have M of these autonomous systems, which is the cardinality of my set V that I have to determine by myself. All right, so this is just a copy of the problem that we had before. The question is now, does this work, or is this is there a reason why this should work? And the answer has already been given in the 60s by Filipov and Wajewski, where this is a rather abstract result, but what they say is that if the reachable set corresponding to my original control set U is contained in the convex hull of the reachable sets corresponding to the dynamic systems constructed by V, then the set of trajectories corresponding to V is dense in the set of trajectories corresponding to U. So basically I can get away with this because the trajectories are essentially identical. The problem now is that I have a control problem where I have infinitely many switches. So it's a very, very complicated control problem that I need to solve. And the discrete time version does not have infinitely many switches, but if I have now a prediction horizon of length P, then I still have M to the P input possibilities, and this is still a very, or an exponentially increasing problem, or increasing exponentially in cost. But I have a huge advantage because I have now, as the right-hand side of my dynamical system, just a finite set of autonomous systems, right? So I can just pick any off-the-shelf method and replace my right-hand side by the model I wish to use. Let's say a neural network or POD or the Koopman operator and so on. So I've shifted the challenge from creating surrogate models to solving this optimization problem. And this is now the question that we need to answer. How do we solve this problem number 3 efficiently? And we would like to guarantee optimality at the same time. And this now leads to this scheme, this algorithm, where we start with our initial and original problem number 1 in the top left. Here the left column is full state Y, the right column is our reduced state Z. And we have in the top continuous control inputs and in the bottom these integer control inputs, and the algorithm works this way that I move between continuous and integer controls as well as full state and reduced state. So we go from 1 to 2 by this quantization approach by introducing the set V. Then we can go from 2 to 3 very easily using any surrogate modeling technique that we wish. And the question that is left now, how do we get back from 3 to 4 to solve a continuous time problem again that I would argue is easier to solve than the combinatorial one, number 3. And this is via relaxation, which I will be discussing next. But first of all, let's ask ourselves, how can we solve this problem? Obviously, you can solve it directly using total evaluation, maybe, if you do not have too many options. You can use dynamic programming or other methods from integer optimization, but this is every time this is of combinatorial nature, so it increases very rapidly in cost. And the second method is to use a convexification approach. And what I'm doing here is I'm just rewriting my problem number 3 by introducing this additional variable omega, which is either 0 or 1. And I now have a linear combination of all my right-hand sides that I have of all these autonomous systems. And the additional constraints that at each time instances, the omegas need to sum up to 1. This is precisely the problem 3 formulation, just rewritten in another way. And what this now allows me to do is to relax omega to a variable alpha that's not in the set 0 or 1, but in the interval 0 to 1. And this now gives me a continuous problem again with m-1 times p variables in comparison to the dimension of u times p variables for the original problem. So, well, it depends on how you pick v and how the dimension of u is, but I would argue that this is of similar complexity than the original problem. And the final step is then either to apply this relaxed solution directly to your system again, which works for control affine systems, or otherwise to use a rounding technique to get integer controls back that you can then apply. And this is essentially the algorithm that we use. We now would like to discuss a few steps. How can we include error bounds to guarantee stability, for instance? Well, I will not be discussing stability, but this is the outlook, let's say. So the rounding that I discussed at the last step was introduced by Saga, Bock, and Deal. And it is, well, I'm not going into the specifics mathematically, but what you can think of it is that it works as some kind of rounding with memory. Meaning that if your alpha value is 0.8 all the time, then you will round to 1 80% of the time, and you will round to 0 20% of the time. So that on average, you reproduce your input. And if you have now a time variant signal, then the rounding varies also in time. But the mathematical result is that you can bound the error between the omega and the alpha, or the integral error between these two quantities, by the number of decision variables m and your time step. So if you do this time step small, then essentially you have related control signals. And this now allows us to show a quite nice result, which says that if I have a control trajectory u, so a continuous control input to my system, and this creates a trajectory y, then there always exists a trajectory u bar from my finite set v, for which I can bound the error between these two trajectories. So if you give me a u, I can find a u bar from my set v, and the error can be bounded by these constants, which I will not discuss in detail, but it depends on how I pick set v. It depends on the time discretization and also on the deviation in the initial condition, which is due to Grünwald's lemma. And then you have this exponential error bound. And by very simple extension, you can then show that if you solve the optimization problem 2, then you can bound the optimal function value of the optimum of your problem 2 to the optimum of problem 1. So you have really, you can quantify how large the error is that you introduce. And this can now be accompanied with a modeling error that we need to have. So this is where I am going to introduce a large assumption, because as I said in the beginning, there exist surrogate modeling techniques with error bounds. And this is what I'm going to assume now, that I can bound the error between my true systems, so f of my true right-hand side phi of y, and the surrogate model phi r of z by some value e, which may be constant or may depend on the time discretization, whatever. I'm just saying it has to be bounded. And this can be done, for instance, for POD or for the Krugman operator. And if I do this, I can construct a time-dependent version of this error, which is just a recursion of the formula that I had above. And let's make this more precise. If we assume that our function f is the identity and the error is depends on the time step delta t, then we get an error of this form where we have this recursive error which decays exponentially, which is, I would say, quite common in dynamic systems. But we can have such an error bound. And this now allows us to bound the errors not only between problems 1 and 2, which I had earlier, but between problem 1 and 3. So the reduced order model version, where I have just now a concatenation of these two errors. So the top line is what I had before, and the bottom line is what is added by the surrogate modeling error. And in a next step, without going into the specifics here, I can, well, before I go to the next step, I would like to say that if I pick V appropriately, then this first term EV goes to 0. If I pick the time step delta t sufficiently small, then this second part goes to 0. And what's left is only the modeling error between problems 3 and 1. And now this allows me to close this loop and have a similar error estimate on the surrogate modeling side between mixed integer and continuous control inputs. And I'm not going to discuss the details here. You get error bounds that have additional terms due to this second mixed integer transformation. And you can then exploit, for example, linearity of observable functions if you have these, or you can exploit control affine properties of your dynamic systems, and these then allow you to step by step further reduce or sharpen the error bound that you have. So before I get to the results, just one quick recap of what we had. So we started with a continuous problem number 1. Then we quantized this, introduced surrogate models off the shelf, for which we do have error bounds, and then use this relaxation and sum up rounding approach to go back to a continuous optimization problem. And then we can have different error bounds depending on system properties that we can use, for example, linearity of the observable function or control affine properties. And this can now be applied to quite a large number of systems. Let's, for example, consider the Duffing equation for starters, where I've already introduced the surrogate version of this equation by adding this epsilon parameter. And we have, you see, this is control affine, so the U enters linearly into the system. And, well, I'm not going to discuss the specifics here, but what you can do is, due to this control affine property, and this error bound is a constant in this case, and for time integration, constant times delta t, you have this exponentially deviation of the trajectories of the true system and the reduced system that I had on a few slides back. And I can now use this surrogate version, so this is the version of my right-hand side, to control the system, to stabilize the origin. And what you see here is the black lines are dashed as state 2 and solid as state 1, or the y1 and y2. And you see a constant offset, which is due to the constant error that I had. But otherwise, we see a really nice control performance. The U is also very similar, at least for the control affine case. The red one is this rounding procedure. And what's most important is that you see that we can prove these error bounds, either the blue cones for control affine systems, or the red cones for the most general version of my problem formulation. But in the control affine setting, you see that these bounds are quite nice and can be used really easily, or can really well used for MPC, for instance. And this is what I'm going to do now in the results section. So this basically brings me to the end of my talk. I will just go into details of 2 examples after this. What we have done is we have implemented a large number of systems, from ODEs like the Lorentz systems over PDEs like the Burger's equation or Navier-Stokes. We have stochastic systems or delay differential equations, and we have used different surrogate modeling techniques like the Koopman operator, proper orthogonal decomposition, different neural network architectures, and so on. So you see that we can just put this together for quite a large number of systems. And, well, the plots are now rather small, but what I would like to convey here is that this can be used quite easily, because you just need to plug in a surrogate modeling system, and then the whole procedure can be applied to arbitrary systems. And 2 examples maybe how this works for the Mackey-Glass equation, which is this delay differential equation for blood cell production, where we have these 3 input levels, minus 0.2, 0, and +1. And we use a reservoir computer as our surrogate model with 3 different output layers, because in reservoir computing, you only train the output layer. So we have 3 output layers corresponding to these 3 autonomous systems. And we can then easily stabilize the constant function 1 with our modeling approach using just data collection and applying this algorithm. And the final example is the Lorentz system, where I would like to discuss this linearity of the control input. So if you use linear control, and then EDMD is a numerical version for the Koopman operator approximation, then you see that both this continuous control input as well as the sum up rounding, which now gives this blue blob because the switching is quite fast, both work equally well. But if you have a non-affine control input, you see that this linear interpolation between different systems does not work so well anymore, but the sum up rounding still does the job, as it has essentially no requirements for my system. Okay, and this brings me to the end of my presentation. I would like to thank you for your attention and, well, point you to the code. So we have published the numerical implementation. If you're interested, you can just download it. And otherwise, I'm happy to take any questions.
Thank you, Sebastian, for the very interesting talk. And there's already the first question coming from the panelists. Bernd, please go ahead.
It looks like your idea of discretizing the actuation commands is very promising, and I can see why. Can you give an idea which problems become solvable, which were not solvable before?
Oh, well, if you think about
so where do you gain maybe a factor 10 in computing power, or where certain things become only doable with your approach?
Yeah, well, what I need to do is what I have done, let's say, is in this case, I've used MPC to solve all these problems. So I need a model, if I want to do this in real time, that is really fast. And for example, what we have done for the Navier-Stokes equations, we have used a Koopman operator-based model, which is 5 orders faster than solving the Navier-Stokes equations. So I would say for complex systems, the model efficiency is really the key. So I think I would argue that we could use MPC on the Navier-Stokes equations without any system knowledge, because what we have done is only measure lift and drag of the cylinder and construct a surrogate model for only lift and drag. So we have no information of the flow physics. We have just measurable quantities, so the forces acting on the cylinder, and could use a highly efficient, well, in this case LSTM, but we have done it with Koopman operator as well, model for real-time control. So I think, well, the decoupling between the full state of the system and your data-driven model is an advantage. And, well, to the quantization, I'm not quite sure. I would say all control affine problems are easily solvable because you can just take the control bounds. I would argue that for nonlinear control inputs, there are many other approaches fail. For example, this DMDC approach, where you have an edit or this autonomization, this works really nicely for control affine systems, but it fails for nonlinear control inputs. And this is where we have been successful.
What about many inputs? Suppose you have, say, a ramp, and you have something like 10 actuators or maybe 100 actuators according to the ramp. At this point, suddenly the discretization gives rise to an exploding number of discretizations.
I agree. Well, the complexity is linear in the number of control inputs that you choose, right? So if this is in the Navier-Stokes example, we have U is -5, 0, or 5, so 3. If you have many inputs, but you can limit the number of inputs from your set V, then you can get hold of the complexity. If you want to really have the full potential of the entire control space, then I would agree that this increases in complexity rather quickly. But if the controls are not all independent, but you can maybe say that, well, 2 of them need to be positive.
You need a correlation, otherwise the dimension explodes.
I would think so, yes.
Thank you.
Sebastian, I would like to add a question from my side. How do I parameterize my controls? Because you have started off very nicely saying, okay, I want to choose a control function. And now you have only using a parameterization using the control constraint, but I could use I could parameterize a control function also in a function space, right? Choosing some basis functions. Would this also work here?
Well, that's an interesting question. I would, well, numerically you could do this. I would say this is certainly possible, because you just need, if you want to represent it in some space, what you need to do is you need to collect data corresponding to the control signal that you choose, and then construct surrogate models corresponding to this. I'm not so sure or right away about the error analysis, so if this goes through, but I would argue that anything that you can apply to the system and collect data for, this is viable.
Okay, thanks. Are there further questions? I'm looking in the Q&A panel and the chat. This doesn't seem to be the case. Thanks again for a very interesting talk, Sebastian. And I would take 2 minutes to wrap up today's seminar. And it has been a very intense afternoon. We thank, as organizers, all speakers for providing very interesting insights which cover quite a broad range. Now, there's a natural question which Bernd has been posing before we even started the seminar, because Bernd has been asking, so how does this IFAC virtual seminar series continue for the IFAC TC on optimal control? And since this is the very first edition, I replied a few hours back that we are still in a transient phase, but I'm very positive seeing the response and the lively discussions we have seen today. So we are currently evaluating how we continue, but the general idea is that if you have an idea for what should be the topic for the next seminar, then please drop an email either to Lars or me, and we will see what we can do and how we can arrange things. In general, we try to have 2 to 3 of these seminars per year, and I think this was a very good start here. If on top you have comments and feedbacks for today's virtual seminar, please feel free to contact Karl and me, who have been in charge for organizing this one. I think once more, thanks to all speakers for very nice contributions. And by this, we will close this seminar. We had a few questions in the chat. The recordings will be available. We'll try to do this, and you will see on the usual social media channels when these recordings are available. Thanks to all.
Thank you. Bye.
Thank you. Bye-bye.
Thanks to all the speakers once again from my side as well. See you soon to everybody, including the audience, of course.
Yes, thank you very much to everybody.
It was a great seminar. I really enjoyed it.
Yeah, me too.